Hello, and welcome to the Snoozy Scientist, where we wander softly through the mysteries of our world, one sleepy yawn at a time. Tonight, we're stepping back 56 million years ago into an age when Earth caught a fever it couldn't shake. The planet simply would not stop warming. This was not a passing summer, nor one of the gentle thaws between ice ages. This was something far deeper. It was a planetary heat that rose from within and reshaped everything. Imagine lush rainforests stretching into the Arctic Circle. Imagine animals shrinking just to survive. Imagine the deep sea, once rich with oxygen and life, turning dark and suffocating. Creatures that had thrived for millions of years vanished without a trace. There were no engines, no factories, no human hands to blame for the warming. This was a transformation driven entirely by nature, unstoppable, uncontrollable, and vast. It was no brief anomaly. This fever lasted for over 100,000 years, during an event scientists call the Paleocene Eocene Thermal Maximum, when Earth's temperature rose by about 5 degrees Celsius. Life faced an ultimatum: evolve, flee, or vanish forever. But if a change so small could rewrite the story of life, what might it mean for us now, standing on the edge of another warming world? And if warmth once pushed Earth so close to collapse, why did the planet ever cool again? What hidden forces pulled it back from the edge of its own heat? Tonight, we'll drift softly into that forgotten age of fire, when Earth warmed by 5 degrees Celsius and life barely endured. But before we begin, if you find comfort in these quiet journeys through science stories, it would mean so much if you gave this video a gentle like and tapped subscribe. It helps more curious minds find their way to this peaceful corner of the internet and reminds the algorithm that sleep and science belong together. And if you'd be so kind, tell me in the comments, where are you winding down from tonight, and what time is it there? I love seeing how far across the world these sleepy explorations travel. Now take a deep breath, let your shoulders relax, and together, let's drift into the fevered past to witness the last time warmth nearly ended life on Earth. Before the fever, Earth was calm. The air was thick with warmth, but it was a steady, gentle kind of warmth, one that wrapped the planet in life. The world had settled into a rhythm after the great extinction that ended the age of the dinosaurs. What came after was quieter, slower, a planet breathing evenly again. Forests covered nearly every stretch of land. The oceans were deep and clear, and the air carried the scent of moisture and growth. It was a time when balance still ruled, when what rose into the sky always found its way back down again. The continents did not look as they do today. South America was drifting away from Africa, and North America still brushed against Europe across a narrowing sea. India was racing north toward Asia, preparing for a collision that would one day lift the Himalayas from the ocean floor. In the far north, Greenland had not yet frozen. Across these lands, rivers wound through endless forests, and coastal swamps shimmered beneath thick, humid skies. The poles were cool but not frozen, and the line between seasons blurred into a soft, steady climate that rarely changed. In this world, the Paleocene forests reigned. Towering trees stretched high into the air, draped with ferns, moss, and vines. The canopies were alive with rustling leaves and the quiet movements of early mammals. They were small creatures, many no bigger than modern-day cats. Some climbed trees in search of fruit, others foraged along the forest floor, their soft paws pressing into the damp earth. Above them, birds filled the air with sound. Their wings caught the light as they darted between branches, their calls echoing through the heavy air. It was a time of recovery, a time of beginnings. The oceans were as alive as the forests. Beneath the waves, coral reefs spread across shallow waters, and schools of fish swam through shifting curtains of light. Tiny shells and plankton drifted gently in the currents, forming invisible highways of life that carried food from one end of the ocean to the other. The deep sea was full of creatures that had survived catastrophe, each adapted to a world of darkness and slow motion. Layers of cold and warm water mixed in a quiet exchange that kept oxygen flowing through the depths. The sea breathed like a living thing, in balance with the air above. Volcanoes dotted the horizon, but they were calm too, their fire mostly hidden beneath the crust. Now and then, one would sigh smoke into the sky or spill a river of lava down its slopes, but these were ordinary acts for a restless planet. Their breath of ash and gas was small, easily folded back into the planet's cycle. The carbon they released was captured again by plants, drawn into their leaves and stems, and carried down into the soil when they died. It was a perfect circle, slow and sure, keeping air and ocean in harmony. Rain fell often. It came in soft curtains, feeding the trees and rivers. The ground drank it easily, and the cycle began again. Water rose, condensed, fell, and rose once more. Every drop had a place. Every piece of the system worked as it should. In this world, there was no rush, no imbalance, no warning that something fragile was being held together by forces that would not last forever. The days were long and gentle. The air carried the smell of damp earth and growing leaves. Insects hummed in the heat, and seeds drifted lazily through shafts of sunlight. The early mammals lived in the shadows of great trees, unaware that their descendants would one day inherit the world. They had no sense of time as we do, no reason to imagine the planet could change so suddenly. To them, this was simply how the world had always been, and how it would always remain. In the oceans, layers of tiny shells fell to the seafloor, settling into soft blankets of white that would one day turn to stone. Each shell carried a record of the water it once floated in, holding silent numbers written in isotopes of carbon and oxygen. They marked every breath the ocean took, every slight shift in temperature, every balance maintained. Deep below, the sediments stacked themselves neatly, patient and unbroken, unaware they were keeping a diary for the scientists of the far future. Life was not peaceful because it was free of struggle, but because the struggle was stable. Predators hunted, prey hid, storms came and went, but the boundaries of the world stayed firm. Temperatures did not swing wildly. Carbon moved slowly between air, land, and sea, never straying too far for too long. If you could stand anywhere on that ancient earth, you would feel the same steady pulse beneath your feet, the same rhythm that had carried life through millions of years. It was a warm planet, but not a feverish one. The warmth fed the forests, stirred the rains, and kept the oceans alive. Every process supported the next, forming a web so intricate that it seemed unbreakable. Yet within that web, unseen and unnoticed, small changes were beginning to gather. Deep beneath the surface, forces were shifting, setting the stage for something vast. But on the surface, no one knew. The forests whispered softly in the wind, the oceans moved in quiet rhythm, and the world, unaware of its own fragility, continued to breathe in perfect balance. It began so quietly that no creature could have noticed. The sun rose as it always did. Winds crossed forests and open water with their familiar breath. Rivers kept their steady roots to the sea. Yet under the crust, far from leaves and light, the planet's deep machinery shifted by a small but fateful amount. Along a long seam of young ocean between ancient continents, hot rock pressed upward. Magma threaded itself into buried layers rich in old plant matter, the kind of carbon that had slept in darkness for millions of years. Where heat met these black rocks, gases formed and escaped. Some rose straight from volcanism, and some were made as the baked sediments released what they had stored. The air took in those invisible additions, mostly carbon dioxide, and held a little more warmth than it had before. The change was slight at first, too slight for eyes or ears, but the balance that had kept Earth steady began to lean. We would only learn what happened long afterward, in a thin band of stone, where the planet's chemistry flips in an instant. For the beings alive then, there was no sign to read, only seasons that felt a touch longer, nights that did not cool as deeply, and seas that rested a little warmer at their skin. Warm surface waters touched another hidden store. Along the continental slopes, where shallow shelves drop into blue depths, the cold and pressure had locked methane into delicate lattices within the mud. These frozen cages, held together by chill and weight, were stable while the water around them stayed cold. As warmth crept downward, the cages loosened. Methane slipped free, first in small threads, and then in broader trails that rose through the water and reached the air. Methane holds far more heat than carbon dioxide while it lasts aloft. Its release nudged the scales further, adding speed to a change already underway. The loop was simple. Warming loosened more methane deepened the warming. At the surface, the ocean began to take in additional carbon, as it always had, but the load grew. Chemical buffers stirred to meet the task. Yet even a great sea has limits when pressure rises too fast. Each new bit of carbon in the air shaded the planet's windows a little, letting sunlight in while slowing the escape of heat. With each season, the long curve bent a little higher. Air moves heat and moisture around the world, and it responds to small shifts with large patterns. As the planet warmed, pressure belts and storm tracks drifted from the places they had favored, not by great distances and not at once, but enough to change where rain fell and where it paused. Some coasts began to feel heavier, slower weather. Other interiors felt stretches of dry air that lasted longer than memory. Rivers still ran, but their stories began to change as the sky decided to linger or to pass by. The seas carried their own messages. Warm water holds less of many gases than cold water does, including oxygen. As the top layers grew warmer, they mixed less readily with the cool and heavier depths. The surface lingered in its light and warmth, while the deep kept its weight and stillness. This gentle separation, felt first as a tendency and not as a shock, set the stage for larger stresses that would come later. Life that depended on mixing currents did not yet fail, but the first conditions of strain were in place. On land, the earliest signs were quiet. Growing seasons lengthened by small steps. Plants took advantage of the extra carbon in the air, using it to build tissue as they always had. Some regions welcomed faster growth. Others began to feel the cost when water did not arrive on the old schedule. Animals followed food and shade. Insects expanded their ranges in years that did not cool as much. Seeds found new places to take root. None of it seemed like an upheaval when viewed up close. It was a gentle tilt that over time moved whole maps. Within a few thousand years, a span that is brief in the language of rocks, the average warmth of the planet had climbed by degrees that matter to chemistry, to currents, and to life. The climb did not stop. Magma continued to heat buried organics in many places. Vents on the seafloor and faults on land found paths for gases to rise. The seafloor gave back methane where the cages could not hold. The air carried the added heat around the planet, and the ocean accepted as much of the burden as it could. The carbon cycle had always been a patient conversation between stone, water, air, and the living world. Weathering drew carbon from the sky and moved it to rivers. Shells and skeletons locked some of it away as they settled to the bottom of past oceans. Burial kept it from the day. Volcanism returned it in slow, long breaths. In this age, the breaths quickened. Returns came faster than removals. The old dialogue slipped into a monologue, and the listener was the warming sky. This was not the kind of change that sends a single loud signal. It was a soft insistence, season after season. The surface ocean grew a little less able to soothe the air. Cloud bands found new places to gather. Nighttime lost some of its old relief. The planet, still green and blue to any eye, began to keep more of the sun's gift than it had the year before. No creature watching a horizon could have pointed to the source. The days still had their sunlight. The winds still carried scents of pine, salt, or dust, depending on where one stood. The first consequences arrived as tendencies, not catastrophes, yet the conditions that would favor larger changes were already in motion, set by deep heat, by carbon rising from stone, and by warm water coaxing ancient gas from its fragile hold. Early pulses of carbon likely came from magma intruding organic rich rocks, and from methane released as warming seas destabilized frozen hydrates. The sum of those pulses altered the atmosphere just enough to tip long standing balances. With each passing year, the planet kept a little more energy than it let go. With each passing year, the great circulations of air and water adjusted in small but telling ways. The story that would reshape forests, coasts, and seas had begun, not with a roar, but with the quiet turning of hidden gears. It began without a sound. The sea did not rise in anger or flash with color. It looked the same as it always had, its surface folding gently beneath the light. Yet within that calm, a rearrangement had begun, so small it could only be seen in the language of molecules. For millions of years, the ocean had been Earth's quiet accountant, balancing the exchange of carbon between air, land, and life. Every gust of wind that ruffled its surface carried a faint transaction, a little carbon moving in, a little carbon flowing out. It was a system so finely tuned that even small changes were absorbed and spread across its vast body. But now the balance was failing. The air above held more carbon than before, and the ocean could not help but breathe it in. When carbon dioxide dissolves in seawater, it reacts with the water itself, forming carbonic acid. The name sounds harsh, yet this acid is gentle and silent. It does not bubble or sting. Instead, it changes the proportions of invisible ions that give seawater its life-sustaining chemistry. Hydrogen ions multiply, and they seek out carbonate ions, the same ones that corals, clams, and countless tiny plankton use to build their shells. Each pairing steals one more building block from life's supply. The sea's chemistry begins to lean toward acidity, molecule by molecule, like a great equation drifting out of balance. It is a process both simple and relentless. The more carbon the ocean swallows, the more its internal chemistry shifts. In the upper layers, where sunlight glimmers through and waves mix the water, the reactions happen quickly. The ocean's natural buffers, compounds that once steadied its pH, begin to weaken. The sea is vast but not infinite. When too much carbon enters too quickly, even this enormous reservoir starts to change in measurable ways. Far beneath the surface, where pressure deepens and currents move like slow rivers, the chemistry shifts more slowly, but with profound consequence. Here, the concept of the saturation horizon becomes real. Above this depth, calcium carbonate, the material of shells and skeletons, can remain solid. Below it, the water is too acidic, and shells begin to dissolve. As carbonic acid increases, the horizon creeps upward. Depths that had once been safe for shell-bearing life now fall into the zone of corrosion. It is not an instant collapse, but a quiet retreat, a slow migration of stability toward shallower water. The reaction continues in every corner of the ocean. Hydrogen ions drift, combine, and separate in endless patterns, each repetition drawing down the sea's ability to build. Corals in the warm shallows find it harder to lay their skeletons. Pteropods, the delicate sea butterflies that flutter through open water, must spend more energy maintaining their thin shells. The change is invisible to the eye, but heavy in consequence. What had once been an effortless chemistry becomes work. In coastal waters, rivers bring minerals that help neutralize some of this new acidity, but the relief is small and fleeting. The load from the air above continues, and the buffers are consumed faster than they can be renewed. The delicate balance between carbon dioxide, bicarbonate, and carbonate ions keeps shifting toward the forms that cannot sustain shells. The ocean's role as a cradle for life begins to strain under the weight of its own generosity. For creatures suspended in the upper layers, the difference begins as a whisper. They grow slightly thinner shells, or none at all. Some drift longer before sinking, others settle sooner than they should. The ocean still appears whole, but its foundation is quietly eroding in chemical form. Even the air above feels the effect. As the ocean absorbs more carbon, it leaves less in the atmosphere, slowing the rise of temperature for a time. Yet this exchange carries a hidden cost. The carbon is not destroyed, only stored in a new form that alters the sea's nature. With every breath of the planet, more of this invisible acid seeps into its waters. Scientists call this process ocean acidification, but that word does not capture its subtlety. It is not an external poison or a single event. It is the ocean responding exactly as nature dictates, an inevitable reaction between carbon and water, following the laws of chemistry that have never changed. The tragedy lies in the pace. What once unfolded over hundreds of thousands of years was now occurring in a geological instant. Imagine standing on a cliff beside the sea during that distant age. The waves would still rise and fall in their rhythm. The scent of salt would still hang in the air. You would see no sign of the transformation below. Yet beneath your feet, the world's largest living system was shifting its structure. The balance between the ions that build and those that dissolve was tilting toward dissolution. The deep water, heavy and slow to mix, took longer to register the change. But as the altered chemistry from above sank and spread through ocean circulation, it began to touch places that had been stable for eons. The layers that once protected the deep from surface disturbances started to fade. It would take centuries for the full reaction to reach the abyss, but by then the surface layers were already different from what they had been. The numbers that define this transformation, pH levels, saturation states, carbonate concentrations, sound clinical on paper, yet behind each is a shift in the invisible architecture of life. The ions that shape coral reefs, shells, and skeletons are the same that influence the ocean's color, its clarity, and its ability to nurture. As they change, everything that depends on them changes too. The sea did not rebel, it simply obeyed the chemistry it had always followed. Each wave that touched the air took in a little more carbon dioxide, and each reaction between water and gas created one more trace of acid. The process continued without pause or mercy, indifferent and precise. What began as invisible chemistry would soon be written into the deep, where entire communities vanished and the seafloor changed color. It began with silence, not the kind that follows a storm, but the kind that settles before one, when the world feels poised and waiting. The change that was reshaping the earth had now reached the air itself, moving through it like a whisper through glass. Carbon rose unseen, joining the sky in a slow, steady drift. The earth had always breathed in this way, exhaling through volcanoes and fires, inhaling through forests and seas. But this time, the breath had deepened. The sky was drawing in more than it could release. Each molecule of carbon dioxide that entered the atmosphere lingered a little longer than before. The sunlight that touched the ground still returned upward, but it no longer escaped freely. The heat that once fled to space began to circle back, caught in the growing weave of greenhouse gases that wrapped the planet like a thin invisible blanket. The warmth that reached the ground now stayed there, humming softly in the air, raising the temperature of the surface, by small but lasting steps. At first, nothing looked different. The wind still traced its old paths across the continents. Clouds still gathered, broke, and drifted on. But the character of the air was shifting. It was becoming heavier with vapor, richer in energy. Days grew warmer, and nights began to hold on to their heat. The difference between the two blurred until the planet no longer cooled in the quiet hours before dawn. This new warmth changed the rhythm of the sky. Layers of air that had once moved in clean, predictable bands began to mix in unusual ways. Rising heat from the surface lifted moisture higher than before, feeding the growth of towering cloud systems that stretched deep into the atmosphere. The upper air thinned slightly as the lower air thickened, creating uneven gradients of pressure. These gradients guided the winds, and when they shifted, so did the world's weather. In the tropics, the belt of circulating air known as the Hadley cell began to swell. The edge of the tropics, once sharply defined, crept farther toward the poles. Jet streams that had long raced around the planet in narrow lanes started to wander. They slowed, looping and folding back on themselves like a river trapped in its own meanders. Where they lingered, the weather lingered too. The air grew restless, not because it moved faster, but because it no longer knew where to go. Systems that had once drifted quickly from west to east now stalled, holding their heat or their chill over the same ground for weeks. The boundaries between climates softened. The dry zones reached into places that had been green. Moist air, trapped beneath layers of warmth, drifted without rising. Nights felt strange in this new world. The cooling that had once swept through forests and deserts never quite arrived. The warmth of the day remained, pressing down gently, even in darkness. Dew formed in thicker films on leaves, and the scent of soil lingered longer before morning came. It was as if the air itself had forgotten how to rest. The chemistry of the atmosphere changed alongside its motion. Water vapor increased, amplifying the very process that had created the warming. It was a feedback written into the laws of physics. Warm air can hold more moisture, and moisture is itself a greenhouse gas. The more the air warmed, the more water it gathered, and the more it trapped heat. The balance that had once kept Earth's temperature steady began to spiral gently upward. The surface winds responded in kind. Sea breezes pushed farther inland. High altitude currents curved and wavered where they had once stayed firm. The pattern of storms and calm zones shifted slightly north and south, tracing the changing lines of temperature. Air masses that had always remained separate began to meet. Where warm and cold touched, new kinds of turbulence were born. Lightning flashed more frequently, not from anger, but from abundance. The air's rising humidity meant more charge separation, more potential energy waiting to discharge. Thunder followed, its deep roll muffled by the denser, wetter atmosphere. Even sound traveled differently now, moving through the thicker air with a low, lingering tone. From above, the planet's colors were beginning to fade. The blue of the atmosphere, once sharp and bright, softened beneath a constant haze. High cirrus clouds stretched across the equator in broad, unbroken sheets, reflecting sunlight by day and trapping warmth by night. The poles glowed faintly in the infrared, releasing the remnants of heat that had made its long journey from equator to ice. The Earth's skin shimmered with energy that could not fully escape. The shifting of air also meant a shifting of seasons. Spring arrived earlier in some places and later in others. Autumns stayed warm far longer than they should have. The air, rich with carbon, fed plants that grew with sudden vigor, yet the pattern of their blooming became uncertain. Migrating animals followed cues that no longer matched the weather ahead. The atmosphere's quiet alteration was writing new rules for everything that depended on it. High in the stratosphere, ozone and water vapor began to dance in different proportions. The rise of temperature in the lower atmosphere changed how gases moved between layers. Winds that once spun steadily along the edge of the poles faltered, loosening their grip. The barriers between cold and warm air thinned, letting tropical heat reach farther north and south. The sky itself seemed to breathe slower now. Every cycle of air through the lungs of the planet took longer to complete. The exhale of heat to space came less freely. More energy stayed trapped within the lower layers, waiting for a path that no longer opened as wide as it once had. The atmosphere, thick with both vapor and warmth, became a slower, heavier engine. The earth was still beautiful from above, but softer in its outline. Continents glowed beneath a haze that blurred their edges. Clouds stretched in languid ribbons across the oceans. The air had become a keeper of warmth instead of a messenger of balance. As the sky thickened and patterns slowed, water began to forget its old routes, a change that would soon be felt in the rains. In the far north, where silence once stretched from horizon to horizon, warmth began to seep into the frozen ground. It did not come with fire or thunder. It came slowly, as though the world were exhaling after a long breath held in ice. The transformation began invisibly, carried in the softness of air and the slow retreat of frost. What had been a white, glittering plain for millions of years started to darken. The light that once scattered off endless snow now sank into thawing soil. The first change was small. Mosses crept over ground that had never known their touch, forming thin carpets of green that spread across meltwater pools and thawing slopes. Grasses followed, taking root in the damp earth. Then came shrubs, their roots delving into layers that had slept for ages beneath permafrost. Each spring reached deeper than the last, and with it came plants that had never before seen the Arctic sun. Fossil pollen tells the story clearly. Within the ancient sediments of high-latitude lakes lie grains from birch, alder, and even palm. Tiny remnants of leaves, preserved like delicate paper, show veins shaped for warm, humid air. Rings in buried wood record summers long and mild, winters short and wet. In those same layers are the bones of crocodiles and turtles, creatures that could not have lived in cold. These fossils are not scattered oddities. They are proof of entire ecosystems that once flourished at latitudes where, today, ice reigns for most of the year. To imagine it is to see a world almost unrecognizable. The horizon that now glitters white would have shimmered in green and brown. Forests grew where glaciers once pressed against the sea. Trees rose along riverbanks that wound slowly through low valleys of mud and fern. The air, thick with moisture, carried the buzz of insects and the scent of wet soil. During the endless days of summer, the sun circled low, never setting, pouring a golden light that seemed to hum against the leaves. Those forests were rich with life. Along their shaded floors, early mammals foraged among ferns and fallen wood. Turtles glided through warm, sluggish rivers. Crocodiles slipped into quiet backwaters to wait for prey. Fish moved beneath floating mats of vegetation, and amphibians croaked from the shallows. The Arctic had become a swampy refuge, a mirror of what today might be found thousands of kilometers to the south. Snow and ice, once the Earth's brightest mirrors, had melted away. Where they had reflected sunlight back into space, the land now absorbed it. Dark soil, open water, and dense vegetation drank in heat and kept it. This shift in brightness, the loss of albedo, became a new engine of warming. Each degree of thaw exposed more ground, and each patch of exposed ground gathered more warmth. It was a cycle that fed itself, a quiet feedback that helped sustain the fever of the planet. The transformation altered not only what grew, but how the planet worked. The polar regions had long acted as anchors of cold, stabilizing winds and currents. Once they warmed, that balance faltered. The gradient between equator and pole, which drove global circulation, weakened. Air that had once flowed swiftly across latitudes slowed and wandered. Jet streams shifted. Ocean currents that depended on differences in temperature and density began to change course. The Arctic had always been the planet's thermostat, but now it had lost its cool touch. Even light itself seemed different. Without fields of ice to scatter it, the atmosphere thickened with haze and moisture. Sunlight took on tones of amber and gold, glowing through veils of vapor that hovered close to the surface. The sky, once pale and clear, seemed softer, blurred at its edges. The horizon no longer shimmered with cold but glowed faintly with heat. Forests grew dense and heavy with humidity. Leaves gathered dew that lingered long into the day. Ferns unrolled from the soil in broad, shining fronds. Insects filled the air with constant motion, their wings flashing in the dim light. Beneath the canopy, the ground pulsed with decay and growth, layers of leaves building up into dark, fertile soil. Each season layered new traces onto the land, and those traces would one day become the pages from which scientists would read this forgotten warmth. Even the long Arctic night, once fierce and deadly, softened. When the sun finally dipped below the horizon for months at a time, the world no longer froze. Temperatures fell, but not enough to still the rivers or lock the ground. The forests waded through the darkness, their roots alive beneath the surface. When spring returned, it came quickly, spilling light across landscapes ready to bloom again. The thaw did not stay at the surface. It reached deep into the foundations of the land. Ancient ice within the ground melted, leaving the soil unstable. Hills and ridges began to shift as the weight of the ice was released. Valleys sank and filled with water. Lakes formed, reflecting the pale sky above. In these waters, sediments began to gather thin layers of mud and pollen, year after year, quietly preserving the memory of this strange new world. Every layer told a part of the same story. Warmth spreading north, vegetation climbing to meet it, life reshaping what had been barren. The fingerprints of this transformation would remain long after the forests themselves vanished. In the pollen grains trapped within silt, in the tree rings fossilized within stone, in the bones of reptiles that basked under a midnight sun, the record of the Arctic's green age endured. No creature living through that time would have known the scale of the change. For them, this was simply life as it was. The rivers ran, the forests grew, the air was warm and thick with the scent of growth. Yet in the quiet processes unfolding there in melting ice, in shifting winds, in the dark soil absorbing sunlight, the foundations of the planet's balance were being rewritten. The Arctic, once the keeper of cold, had turned green. It was not a passing season, but the dawn of a world that had forgotten what it meant to freeze. The warmth did not come as a sudden wave. It crept forward, patient and steady, spreading through the air and into the oceans, touching every continent in turn. It began where heat already ruled, in the low tropical belts, then moved outward until even the farthest corners of the world felt it. Mountains, deserts, and forests all warmed together as if the planet had drawn a deeper breath and decided never to exhale. The change was not loud. There were no storms or flashes to mark its arrival, only a quiet thickening of the air. Day after day, the skies shimmered. Nights no longer cooled the earth. They held the day's warmth close, glowing softly as if the darkness itself had learned to keep heat. The line between night and day blurred, and with it, the rhythm of seasons began to dissolve. Proxy-based reconstructions suggest global mean surface temperatures rose by several degrees, with some regional estimates centering near the low 20s Celsius. Exact numbers vary by dataset and location, but the pattern is unmistakable. The entire planet had entered a sustained warmth unlike anything in millions of years. The Earth's thermostat had turned upward and stayed there. Humidity clung to every breath. Across the continents, air thickened until it felt almost alive. It shimmered in the distance, distorting horizons, making the land seem to ripple under the sun. Even regions that had once been cool and dry found themselves drenched in moisture. The comfort of chill mornings vanished. What remained was a single, unbroken season of warmth. Snow and ice, once the guardians of the mountains, retreated and never returned. Peaks that had gleamed white for ages now stood bare, revealing the deep reds and browns of iron-rich stone beneath. The highlands glowed with a strange color under the sun, as if the ground itself had been fired in a furnace. Rivers that had once frozen now ran without pause, carving new channels through the soil. Rain fell instead of snow, feeding those rivers until they spilled across their banks. The forests expanded, their boundaries stretched far beyond their ancient lines, pushing into regions that had once been temperate. The great equatorial green belt widened until the world seemed wrapped in vegetation. The distinction between tropical and temperate vanished, and the planet moved under a canopy of constant leaves. Trees no longer slept through the cold months or shed their foliage in great, synchronized waves. Instead, they replaced their leaves slowly, continuously, as if the very rhythm of time had changed. As we saw in the Arctic, even the poles were green. The planet's cold anchors were gone, and with them went the sharp contrasts that once defined the world. The winds that had circled the globe for eons shifted their paths. Ocean currents changed direction, guided not by frozen barriers but by open water and heat. The earth had lost its balance between light and dark, between cold and warmth. Rain patterns broke apart. Some regions drowned under heavy downpours that came without warning, while others dried beneath cloudless skies. In some places, the ground softened into endless swamps. In others, it cracked open, revealing dry veins of red soil. The heat drew water upward into the sky, and the sky gave it back in restless bursts. The hydrological cycle had quickened, its pulse irregular but strong. Storms formed easily in this thicker, wetter air. Lightning cut through the clouds with fierce precision. The skies were alive with motion, swirling and reforming across the oceans and plains. Every system of air and water seemed charged, holding more energy than before, as if the planet itself had grown restless. The oceans carried their own memory of the change. Warmth spread across the surface, sealing it from the cool depths below. The layers of water no longer mixed freely. Nutrients remained trapped beneath the surface, while the upper waters gleamed with life that fed on light alone. The sea had become a world divided, the warmth above, the silence below. On land, the transformation reached deep into the soil. In places that baked beneath constant heat, the earth hardened and cracked. Where the rain fell endlessly, the ground turned soft and heavy, stained red by iron that reacted with the humid air. Plants flourished in both extremes, adapting to either drought or flood. Their roots pushed deeper, their leaves broader. The smell of soil and decay filled the air, a constant reminder of how alive the planet had become. Animals changed with it. Those that had depended on cool nights or distinct seasons struggled to keep pace. Some retreated to higher ground, but even there, the warmth followed. Many creatures grew smaller, their bodies more efficient at releasing heat. Activity shifted toward the twilight hours, when the air grew just cool enough to move. Insects multiplied in the damp air, filling the forests with their endless hum. The sound of life became a constant background, as if the entire world had learned a new rhythm. Even the wind changed character. It moved slower, heavier, carrying the scent of wet earth and vegetation. It no longer brought relief, only more warmth, spreading it evenly across continents and seas. The planet had merged its climates together. No longer divided by cold or heat, it had become uniform, steady, and unending in its warmth. Beneath the ocean floor lies a quiet world of ice and gas, where the boundaries of solid and liquid blur under immense pressure. Here, along the slopes of continents and the edges of deep basins, methane gas is locked inside crystalline cages of frozen water. These formations, called clathrates, look like ice but behave like a fuse. They are fragile, balanced delicately between stability and release, holding a vast store of carbon in silence. Methane clathrates form where organic material, buried for millions of years, slowly breaks down in the absence of oxygen. Microbes feed on this buried matter, releasing methane into the sediment. When the temperature is low enough and the pressure high enough, the methane bonds with water molecules, creating solid lattices that trap it in place. These icy structures can persist for eons beneath cold, steady oceans, frozen into the slopes and shelves that rim the continents. But stability is never permanent. When seawater warms, even slightly, the balance shifts. A rise of just a few degrees in the deep can begin to melt those frozen cages. As the bonds break, the methane escapes upward through the sediment, forming tiny plumes that drift toward the surface. Most never reach the open air, consumed instead by microbes that turn them into carbon dioxide. Yet even that conversion adds to the load of greenhouse gases, tightening the loop of warming that started it. Methane is a powerful heat trapper, far more potent than carbon dioxide in the short term. Over a few decades, a single ton of methane can capture many times more heat than the same amount of carbon dioxide. It does not linger as long in the atmosphere, but while it lasts, it amplifies every flicker of warmth. During the Paleocene Eocene Thermal Maximum, this amplification may have tipped the planet from discomfort into crisis. The evidence for this ancient release lies not in visible remains but in chemistry. Across layers of marine sediment and ancient soils, scientists have found a dramatic shift in carbon isotopes, a sudden global tilt toward lighter carbon. Methane, derived from buried organic matter, carries this isotopic signature. When it floods the atmosphere and oceans, it leaves behind a telltale fingerprint that endures for tens of millions of years. Those fingerprints are found everywhere, from Arctic mudstones to tropical clays, showing that the change was both immense and worldwide. Still, the story they tell is incomplete. The records reveal what happened, but not how it began. Perhaps volcanoes were the first to stir, their fires heating buried sediments rich in organic carbon. Perhaps currents shifted, bringing warm water into places that had remained cold for ages. Or perhaps the planet's slow warming simply reached a tipping point where the deep began to exhale. Whatever the spark, the result was the same. Frozen methane began to escape. Picture the seafloor then. In the dark, quiet depths, thin threads of gas slip upward through cracks in the sediment. Here and there, pale mats of bacteria bloom where the gas meets the water, feeding on the methane as it rises. Each bubble that escapes joins countless others, merging into a current of carbon that drifts through the sea and into the air. It is not violent, not sudden, but steady, a silent storm unfolding beneath the waves. Some of the released methane would have oxidized within the ocean, becoming carbon dioxide before ever reaching the surface. This transformation did not spare the climate. Carbon dioxide, once formed, remained in the atmosphere far longer, extending the fever that methane had begun. The more the planet warmed, the more of these hydrates melted. The more they melted, the faster the warming spread. This feedback loop, heat releasing gas. Gas trapping heat is one of nature's most efficient amplifiers. It does not require explosions or cataclysms, only warmth, pressure, and time. As the ocean warmed, it reached deeper into the slopes, destabilizing hydrate layers that had rested undisturbed for millions of years. In some places, the seafloor itself may have slumped as gas escaped, triggering underwater landslides that freed even more methane. The process likely unfolded over thousands of years, yet in the record of geological time, it reads as a single pulse. Modern science has glimpsed this process still at work. Along the Arctic Ocean's continental margins, where the seafloor is warming today, faint trails of methane bubbles rise from the depths. Remote cameras have filmed their shimmer, and instruments detect plumes in places once thought frozen solid. Microbial blooms grow around these seeps, just as they did in the ancient seas. Though small by comparison, these modern escapes are reminders of how thin the line of stability can be. The scale of ancient release remains uncertain. Some researchers believe only a fraction of the stored methane was freed, enough to intensify a warming already underway. Others propose a far larger exhalation, a chain reaction that poured thousands of gigatons of carbon into the air and water. The truth may lie between them, a slow uncoiling of feedbacks, where each process triggered the next, none large enough to act alone, but together enough to remake the planet. Beneath the waves, it would have been invisible to any watching eye. There were no plumes of ash, no thunder from the deep, only a continuous exhalation of gas from the ocean floor. The earth was venting its own breath. The warmth that rose from that exchange spread upward through the air, thickening the atmosphere's blanket. Within a few millennia, an instant in the language of rocks, the consequences reached every corner of the biosphere. Today, methane hydrates still line the edges of continents, containing more carbon than all the world's remaining fossil fuels combined. They rest there quietly, locked in place by the cold and pressure of the deep, but they remember how to release. The clathrates that once turned the oceans into engines of heat are still there, silent and patient, waiting beneath a sea that is slowly, steadily warming again. Around the North Atlantic, the earth began to open. Deep beneath the waves, the crust stretched and cracked as continents drifted apart. Through those fractures, molten rock surged upward, forming one of the largest volcanic provinces the planet has ever seen. These eruptions built vast fields of basalt that still lie buried beneath Greenland, Norway, and the edges of northern Europe. The region is now known to geologists as the North Atlantic Igneous Province, a reminder of the moment when the planet itself seemed to awaken in fire. Magma did not only pour onto the surface, much of it forced its way sideways through layers of sediment that were rich in ancient organic matter, the remains of plants, plankton, and buried soils. As the magma intruded, it heated these carbon-rich rocks to hundreds of degrees, baking them from within. The organic material began to decompose, releasing enormous quantities of carbon dioxide and methane as gas. These gases vented through fissures and cracks, escaping into the atmosphere and oceans. This process, known as thermogenic carbon release, may have been one of the most powerful sources of greenhouse gases in Earth's history. It was not the brief outburst of a single volcano, but a continuous exhalation that lasted for tens of thousands of years. The timing, recorded in the layers of rock and the chemistry of ancient sediments, aligns closely with the beginning of the Paleocene-Eocene warming. For this reason, many scientists consider these volcanic intrusions a strong candidate for the initial spark that set the planet's carbon cycle into chaos. Where methane could amplify warming, volcanic thermogenic release could provide the initial shove. Both mechanisms may have worked together. The fire from below and the ice from the ocean floor, one igniting the other, may have created a chain of feedbacks that accelerated the Earth's fever beyond any natural balance. On land, these eruptions left behind rivers of black basalt that cooled into cliffs and plateaus. In the North Atlantic, they built undersea ridges that would later become the framework of modern ocean basins. But their greatest impact came not from the lava itself, but from what the lava touched. Each intrusion that passed through organic sediment acted like a giant oven, baking and cracking the rocks. Carbon that had been locked away for millions of years was turned back into gas and released. As these gases entered the air, they thickened the planet's natural blanket of greenhouse heat. Carbon dioxide began to accumulate, absorbing infrared radiation and warming the lower atmosphere. The oceans absorbed some of this carbon, just as they always had, but the influx was far greater than their buffering systems could manage. Chemical reactions within the seawater began to change, as earlier chapters have shown, and the seas grew less able to neutralize the rising acidity. The result was a slow but steady rise in global temperatures that spread outward from the oceans to the continents. The evidence for this fiery beginning lies in the rocks themselves. Across northern Europe and Greenland, geologists have found layers of tuff and basalt that match the age of the warming. Beneath them, cores drilled through ancient sediments reveal unusual patterns, organic layers baked to hardness, pockets of gas residue, and minerals that could only form under extreme heat. Even more telling are the tiny geochemical fingerprints within these layers, sudden shifts in carbon isotope ratios that correspond exactly with the timing of the Great Carbon Pulse seen worldwide. Geologists point to timing and geochemical markers in North Atlantic sediments that line up with the onset of the warming, suggesting volcanic activity played a major role. Models of global carbon cycling show that such a pulse could have doubled or tripled atmospheric carbon dioxide within a few thousand years, rapid on geological scales. The warming that followed was not uniform, but it spread through every system: the atmosphere, the seas, the soils, and the biosphere. The surface of the Earth must have trembled with the scale of it. Lava fields stretched for hundreds of kilometers. Ash rose into the air, dimming sunlight in brief, smoky seasons before settling across the oceans. In places where magma met shallow water, it exploded in steam and rock, sending plumes into the sky that carried both dust and gas. Sulfur mingled with carbon dioxide, forming acid rain that fell across distant lands. Yet even this haze could not slow the rising temperature for long. Once the carbon entered the air, its effect was persistent, trapping heat long after the eruptions quieted. The warmth built in layers, one release after another. Forests absorbed the new carbon through photosynthesis, only to return it again when the plants decayed. Soils exhaled more of it, as microbes grew more active in the heat. The cycle became self-reinforcing, each process amplifying the last. The planet had crossed a threshold from which it could not easily return. Millions of years later, the remnants of that ancient fire still shape the Atlantic's edges. The cliffs of eastern Greenland, the basalt plateaus of the Faroe Islands, and the buried lava flows beneath the North Sea all bear witness to that time when the Earth itself exhaled carbon from its deepest layers. The cause of the Great Warming was not a single source, but a chorus of them: volcanic intrusions, thermogenic gases, and the ocean's own release of methane all joined in the same rising note of heat. Yet among them, The evidence points clearly to the fire beneath the North Atlantic as one of the leading voices in that symphony. The warmth that had spread through the air and the oceans began to summon water upward, drawing it from every sea and lake and river. The atmosphere, now swollen with heat, could hold far more moisture than before. Clouds grew vast and dense, their undersides hanging low and heavy. Across the world, the rhythm of rain began to shift. Where once storms had come and gone in predictable patterns, now the sky lingered over the same places for weeks, its breath filled with water that would not stop falling. At first, the change felt like abundance. Gentle rains nourished forests that had already thickened under the new warmth. Every leaf caught the glint of moisture, every fern unfurled in the mist. The sound of dripping water became the background of life. Soil that had long been baked firm by the sun softened into clay, rich and red with iron. But as the weeks turned into months, and the months into years, the rain did not end. The ground began to lose its shape. Hillsides slumped, and rivers that had once traced thin silver lines through valleys turned brown and wide. The land itself began to move. In the tropics, where the air was warmest, the great monsoon systems grew monstrous. Each season they stretched farther, their reach extending into regions that had never known such storms. Rains that had once come in brief pulses now lingered for entire months. The ground could not breathe between them. Forests drowned from below, their roots rotting in the stagnant pools that gathered at their feet. Fallen trunks became bridges for creatures seeking higher ground. New rivers, born overnight, cut across the landscape, carving deep channels that redirected the flow of water toward the coasts. As the atmosphere held more vapor, each storm carried more weight. When the clouds broke, they did so with violence. Curtains of rain fell so thick they blurred the horizon. Rivers swelled until they merged with lakes, and lakes with seas. The boundaries between land and water began to blur. Across low plains, the floods formed vast inland seas that shimmered under the dim sun, their surfaces flecked with drifting debris. Islands appeared and vanished again, whole forests standing like dark islands in the endless gray. Farther north, the same warmth that had turned the Arctic green now filled the air with moisture. What had once been frozen tundra became a labyrinth of shallow lakes and thawed soil. Rains soaked into the permafrost, thawing it further, releasing gases that thickened the planet's fever. Streams braided across the open ground, carrying sediments that stained the water red and brown. Rivers that had flowed gently beneath ice now roared with the sound of stone grinding against stone. The mountains, too, began to change. Without the grip of glaciers to hold their slopes, the constant rain brought them down piece by piece. Cliffs that had stood for millions of years collapsed into torrents of rock and mud, rivers choked with silt, their waters thick and opaque. The sediment they carried drifted to the seas, where it spread across the continental shelves, burying coral reefs and altering the chemistry of shallow waters. The earth was redistributing itself grain by grain. Along the coasts, the combination of rising seas and relentless storms turned deltas into shifting wetlands. The great rivers that drained the continents no longer ended cleanly at the ocean. Instead, they fanned out into wide marshes that pulsed with the tides, fresh water mixed with salt, creating hazy zones where only certain forms of life could survive. In these in-between places, new species flourished: plants with roots that tolerated brine, fish that moved easily between ocean and river, crustaceans that burrowed into the soft, oxygen-poor mud. Each storm altered the surface of the planet. Rains carved new channels through the continents, moving minerals from the mountains into the sea. These sediments fed blooms of plankton, microscopic drifters that filled the sunlit waters. Their brief lives drew carbon from the air, and when they died, their remains sank to the bottom, locking away fragments of that carbon in layers of ooze. Yet even this great cycle, the ocean's way of breathing, could not keep pace with the fever of the air above it. Inland, where the water had nowhere to go, new lakes formed, some shallow and temporary, others deep enough to last for centuries. They mirrored the restless sky, their surfaces alive with constant ripples. Some evaporated between storms, leaving behind crusts of minerals that glittered like glass. Others grew so large they spawned their own weather, drawing clouds that returned their waters as rain. The planet was learning to circulate moisture differently, each basin a new pulse in the global rhythm. The constant rainfall reshaped entire ecosystems. Creatures evolved to live with water as a permanent companion. Mammals took to the trees, building nests above the floodlines. Amphibians expanded into new niches, their eggs carried by the rising streams. Insects thrived in the damp air, forming clouds that shimmered like dust when the rain paused. The boundaries between land-dwelling and water-dwelling life blurred. For millions of years, this was the normal world, green, humid, and restless. Across the continents, erosion became one of the planet's great sculptors. The unending rain stripped soil from hills and carried it down to the basins. The flow of rivers changed speed and course, splitting apart, joining again, and turning plains into braided webs of water. Valleys deepened, their walls streaked with red and ochre. The ancient highlands that had once stood sharp against the horizon began to wear away, softened by centuries of rainfall. In time, even the mountains themselves would feed the oceans, reduced grain by the same element that had once carved them from stone. The rain never shouted, but its persistence carried the strength of anything that endures. It was a sculptor and a destroyer, a quiet force that reshaped the surface of the world. Each drop that fell carried part of the planet's story, a record of heat drawn upward, turned to vapor, and returned as weight. The earth was not burning, its fever had taken another form. The warmth that filled its skies had called the oceans upward, and now the world was learning what it meant to drown in its own breath. The warmth that wrapped around the planet did not simply change landscapes and skies, it began to alter the very shape of life itself. In this new world of dense air and endless summer, survival favored those who needed less. The forests were rich, the air heavy with moisture, but the abundance was deceptive. Plants grew quickly under the elevated carbon dioxide, yet their leaves carried less nourishment than before. Food was everywhere, but it no longer fed as well. For animals large and small, this subtle shift began to decide who would thrive and who would fade. Over thousands of years, evolution started to write a new rule into the bones of its creatures. Fossil records from across the world reveal the pattern with quiet precision. In the layers that mark the height of the Paleocene Eocene Thermal Maximum, paleontologists have uncovered teeth, jaws, and bones that trace a slow but steady shrinking of body size across entire lineages. Horses, primates, rodents, and even reptiles all began to grow smaller. It was not a sudden transformation, but a steady response to a world that had become too warm, too lush, and too unstable for large bodies to endure. Smaller animals held advantages in this new climate. Their bodies shed heat more easily. Their hearts and lungs demanded less oxygen and water. They could live on thinner diets, moving lightly through forests that pulsed with humidity and unpredictable rain. Every generation carried a fraction of this change forward, so small it would not have been noticed by any living creature at the time. Yet in the language of fossils, the difference is clear. What had once been an adult could now fit beneath the shadow of its ancestors' ribs. In the warm forests of what is now North America, early horses were among the first to respond. Their ancestors had stood about half a meter tall at the shoulder, sturdy and thick-limbed, feeding on dense undergrowth. But as the climate warmed, their descendants grew smaller. Within a few thousand years, their bodies had diminished until they stood scarcely as tall as a fox. Their teeth changed too, growing shorter and better suited to the softer, less fibrous plants that now filled the forest floor. They moved quickly, weaving through ferns and palms that stretched toward the golden light filtering through the canopy. Their size was no weakness, it was an adaptation written directly into their bones. Elsewhere, other mammals followed similar paths. Early primates, once the size of modern lemurs, became even smaller, their bodies compact and agile, their hands fine-tuned for climbing slick branches that dripped with rain. In the dense forests of Europe and Asia, they darted through the trees, feeding on fruits, flowers, and insects that thrived in the heat. Their large eyes helped them navigate dim light, for even during the day the canopy blocked the sun. In the evenings, when the air grew slightly cooler, they moved in swarms, their soft steps echoing through the leaves. Small burrowing mammals took refuge in the wet ground of floodplains and deltas, where temperatures were steadier and the soil offered protection. Their tunnels wound through the mud beneath a world reshaped by storms. The earth itself became part of their biology, cool, constant, and safe. These creatures rarely saw the light, living instead in the twilight between air and stone. The pattern extended beyond mammals. Lizards and amphibians grew smaller, their limbs slimmer, their metabolisms faster. Reptiles that once basked under the sun no longer needed to seek warmth, for it surrounded them constantly. Amphibians, ever sensitive to heat and moisture, thrived in the endless wet, their skin adapted to absorb oxygen from water that was often still and low in breath. Insects multiplied in staggering numbers. The forests rang with their movement, the air thick with wings and the hum of constant flight. The sound of life became a soft, endless drone, the pulse of a biosphere adapting in real time. The cause of this great downsizing was not only the heat itself, but what the heat did to the food chain. The rise of carbon dioxide accelerated plant growth but diluted nutrition. Leaves became larger, yet poorer in minerals and proteins. For herbivores, it meant that even an abundance of vegetation could not satisfy their needs unless they consumed more. Smaller animals, requiring less energy, found balance where larger ones could not. Over generations, the forces of natural selection favored compactness. Each birth carried a slightly different body, a small refinement better suited to the world's new demands. The fossil layers that formed during this period capture this transformation in exquisite detail. In Wyoming's ancient riverbeds, the remains of miniature horses and tiny primates lie preserved in thin ribbons of clay. Their bones are delicate, their joints narrow, their teeth fine as grains of sand. Across Europe and Asia, similar evidence appears: smaller skeletons of grazing mammals, each one a whisper of evolution's adjustment to heat. These were not isolated pockets of change, but a global rhythm, mirrored in every continent touched by warmth. The pace of this adaptation was extraordinary. Where evolution usually moves in slow, imperceptible increments across millions of years, these changes unfolded in only a few thousand. It was as if the climate had turned the gears of life faster, compressing the story of transformation into a single geological heartbeat. Not every lineage could keep up. Some species, bound by their size or their slow reproduction, disappeared as the temperatures rose. Others adapted not only in body but in behavior. Nocturnal habits became more common. Smaller creatures emerged under the safety of darkness when the air cooled just enough to breathe more easily. In the dim light of the moon, the forest stirred with motion light, quick and constant. By the height of the Paleocene Eocene warmth, the world had become a place ruled by smallness. Large forms were rare, the landscape alive instead with creatures that fit between shadows, slipping through roots and branches in silence. Evolution had found a new equilibrium. The great giants of earlier ages had given way to the small, the swift, and the adaptable. In this long, humid summer, survival was written in miniature. Every change in bone and tooth, every tiny birth and death, was part of a quiet story, a planet reshaping life to fit the heat it had made. The world had grown restless. The warmth that once lingered near the equator had spread outward, filling the air, the oceans, and the soil. Forests crept north and south, following the heat as it reshaped the face of the planet. Where once there had been dry plains or frozen tundra, there were now humid swamps and endless green. The animals that lived within those forests could not stay where they were. Food had shifted, rivers had changed their courses, and the patterns of rain no longer followed the old rhythms. To survive, they began to move. It started slowly, with small steps across soft ground. Herds of mammals followed the line of the trees, traveling wherever the vegetation was richest. Insects and birds moved ahead of them, spreading pollen and seeds into the untouched lands beyond. As the forest spread, so did life. The journey was not a choice but a necessity, a quiet movement born from instinct. Generation by generation, species began to drift across entire continents. In the northern lands, small mammals moved into territories that had been locked in ice for millions of years. They followed rivers that now flowed freely through what had once been frozen earth. Their tracks crossed mud and silt, paths carved by water that had melted only recently. Behind them, new plants took root. Ferns, palms, and flowering shrubs spread in their wake, carried by the wind, by animals, and by the rain. The planet was reshuffling itself, one small step at a time. Where the continents met, the rising and falling of the seas created new paths. In places like what is now the North Atlantic, chains of islands and shallow bridges appeared, connecting lands that had been separate before. Mammals crossed these corridors in slow, unbroken lines. They moved through the haze of distant volcanoes, across steaming mudflats and dense forests, searching for cooler ground or new sources of food. Tiny horses, already smaller than their ancestors, wandered from what would one day be North America into Europe. They grazed in the open clearings between ancient trees, their hooves leaving delicate impressions in the damp earth. Primitive primates, nimble and curious, traveled along similar routes. They climbed through new forests, following fruiting trees that grew wherever the warmth and rain allowed. Even in the highlands, where the air was slightly cooler, life spread in waves, carried by the constant movement of creatures great and small. Some journeys were longer still. Across the southern hemisphere, species migrated between the continents that once formed the great landmass of Gondwana. These ancient connections still lingered, and for a time, animals could move between what would one day become South America and Antarctica, and even reach Australia. The poles, once cold and lifeless, were now lush with vegetation. Forests stretched across them, green and humid beneath the long summer sun. The creatures that reached these lands found abundance waiting for them. But the abundance was fleeting, always shifting with the patterns of climate and light. The oceans, too, changed in rhythm. Currents that had once carried cold water from the poles now moved sluggishly through a world that had forgotten frost. Plankton bloomed in strange new places, drawing marine life toward the poles where the warmth was still tolerable. Some fish species followed the cooler waters northward, their paths winding through shallow seas that covered parts of the continents. Others vanished from regions that had grown too hot, leaving behind empty ecosystems waiting to be filled. In the sky, the air shimmered with humidity. Birds, many of them descendants of small reptiles, took to the air in long, instinctive migrations. They flew over flooded lowlands and steaming jungles, their routes shaped by the changing winds. The warmth had made the atmosphere heavier, and the air currents moved differently now, pulling flocks into new regions. Each migration rewrote the story of the world a little more. Across the planet, fossils would one day capture the evidence of this great movement. Footprints pressed into the mud would fossilize side by side. Creatures that had never met before now shared the same ground. Bones found in distant layers of rock would tell of species that had spread far from their origins, adapting to new climates, new diets, and new dangers. It was not a sudden event, but a slow wave that traveled through time itself, rippling across centuries. Life was no longer bound by the borders it once knew. The warming had erased many of those boundaries, turning deserts into wetlands, mountains into rain-soaked forests, and coastlines into vast marshes. Everywhere, creatures learned to move. Some followed the rivers that wound through the forests like veins of silver. Others climbed, swam, or drifted, carried by the wind or the flow of water. The planet had become one enormous migration path. Predators moved with the herds, finding new prey in unfamiliar lands. Insects swarmed around flowering plants that had taken root in unexpected places. Amphibians spread across the flooded plains, their calls echoing through the humid air. It was a restless world, full of motion and sound. Every forest, every plain seemed to hum with life on the move. For countless generations, the migration continued. Entire species rose and fell within its flow, their forms slowly reshaped by the journey. The warmth guided them, sometimes gently, sometimes with the force of necessity. It was a time when the earth itself seemed alive in its motion, when boundaries blurred and the old rules no longer applied. The Great Migration was not just a movement of animals, but of the planet itself, a slow rearranging of everything that lived and grew. From the smallest insect to the largest mammal, all were part of the same vast current, drawn forward by the same quiet, invisible force, survival in a world that was no longer standing still. Far beneath the surface, where sunlight had never reached, the deep ocean had always known stillness. For millions of years, it had been a world of quiet balance, where cold water from the poles sank to feed the depths with oxygen, and slow-moving creatures lived their entire lives without ever seeing a horizon. The seafloor was pale and soft, a vast plain of white mud built from the remains of tiny foraminifera that had drifted down from the upper waters after death. Layer upon layer, their shells had settled to form a gentle snow that covered the planet's deepest valleys. Worms and crustaceans moved through it, leaving delicate trails in the sediment. The ocean below had been constant, a realm where time seemed to drift as slowly as the currents themselves. Then the balance began to slip. As the world's surface grew warmer, the circulation that once connected deep and shallow waters began to weaken. Warm water, light and buoyant, no longer cooled enough to sink. The great conveyor that had carried oxygen from pole to abyss slowed, and then, in many places, stopped. Layer by layer, the deep was sealed away from the surface, cut off from the breath that had sustained it for eons. The change came without sound, without motion. The deep sea, always the planet's most patient realm, began to lose its air. At first, the difference was invisible. The water still looked the same, and the slow creatures of the abyss went on with their routines. But the oxygen was slipping away molecule by molecule. It drained from the deep like color fading from cloth. The foraminifera that had once flourished began to vanish, their shells thinner, their populations smaller. Many dissolved before they could ever settle on the seafloor, eaten away by the increasingly acidic water above. What had once fallen as white snow now disintegrated mid-descent, never reaching the bottom. The seafloor began to darken. The soft, chalky ooze that had accumulated for millions of years was replaced by a fine, gray mud. In places where the currents once left ribbons of pale sediment, the layers now grew streaked with iron and sulfur. Bacteria that fed on decay spread through the anoxic water, staining the seabed in shades of black and green. These microbes thrived where oxygen could not reach, feeding on the chemical remnants of what had died. Each generation left behind compounds that would one day be locked into stone, turning the floor of the ocean into a record of its own undoing. The animals that had lived there began to fall silent. Worms that tunneled through the mud came to the surface and stopped moving. Tiny crustaceans curled in their burrows and did not emerge again. Fish, deprived of oxygen, sank slowly through the still water, settling into the dark like lost shadows. There was no struggle, no chaos, only stillness. The deep sea's life ended not with an explosion, but with a gradual erasure, one breath at a time. As the centuries passed, the ocean's chemistry continued to change. Without oxygen, the decay of dead plankton and marine snow created gases that were deadly to most forms of life. Hydrogen sulfide filled the water in faint, invisible plumes, reacting with metals in the sediment to form black layers that still appear in cores drilled from the ocean floor today. These layers, rich in iron and sulfur, are the fingerprints of that ancient suffocation. The ocean had become a chemical machine, converting life into new compounds, reshaping its own memory. In this altered darkness, life reinvented itself. Bacterial mats spread like silver sheets across the sediment, shining faintly when disturbed by the smallest current. They fed on methane and sulfur instead of oxygen, producing chemical light in a world that had forgotten the sun. The soft, constant fall of shells that had once covered the seafloor was gone, replaced by the slow accumulation of decay. The deep had not become empty, only transformed. It was no longer a living community, but a process, a metabolism of the earth itself. The surface above was still vibrant. Warm waters glowed with plankton blooms that covered entire basins in shifting colors of green and gold. Yet every bloom ended in death, and every death drifted down. As the remains sank, they fed bacteria that consumed what little oxygen remained, deepening the suffocation below. The upper ocean, alive with motion, was feeding the silence beneath it. The two layers had become mirrors of each other, one growing richer in life, the other poorer. In places, nearly half of the species that once lived on the deep seafloor disappeared. The record of this extinction is scattered across the planet, in the Atlantic, in the Indian Ocean, in sediments from the Pacific trenches. Each tells the same story of disappearance. The great foraminiferal plains that had once glowed pale under the dim light of remotely sent lamps turned dark. The carbonates that once built the deep's architecture dissolved, and in their place came a heavy, featureless sludge. The deep ocean, which for so long had been the world's most stable refuge, had become its most fragile. The sea's slow metabolism continued, unseen but relentless. The black mud grew thicker. The gases that formed within it rose upward through the stagnant water, their traces carried by faint currents to the surface. There, they joined the atmosphere, mingling with the very carbon that had begun this cycle long ago. The deep ocean had lost its life, yet it still contributed to the planet's fever, returning to the air what had once been locked away beneath it. If one could have descended through that ancient water, the journey would have been haunting. Light would fade to blue, then to black. The air would thicken with stillness, and at the bottom there would be only darkness, a motionless plain stretching into the unseen distance. The silence would not be the calm of peace, but the quiet of a world that had stopped breathing. The rocks would remember this moment. In their thin layers, they would preserve the story with brutal clarity, the shift from white to gray, from calcium to sulfur, from life to chemistry. Long after the oceans recovered, those bands would remain as testimony to the deep's great dying. The record of that silence would one day be read again, far in the future, by eyes searching for how a living planet once lost its breath. The ocean's surface was no longer calm. Warmth soaked through its upper layers, mingling with floods of minerals that washed down from swollen rivers. The water near the coasts grew thick with invisible dust, carbon, iron, and the soft remains of life carried from the land. Each drop became a seed for something larger. Under the heavy sun, in a sea charged with heat and nutrients, life began to multiply at a frantic pace. Microscopic algae and plankton, once delicate threads in the balance of the ocean, now filled it beyond measure. The water turned the color of copper and jade, rippling under a sky swollen with vapor. From above, it would have looked alive, vast sheets of color swirling over the surface, a living mosaic that stretched from shorelines to open sea. But this bloom was not the calm rhythm of a healthy world. It was a restless tide, pulsing between growth and decay without pause. Each hour brought new bursts of activity. The sunlight poured down through the haze, striking layers so dense with organisms that the sea lost its usual blue. It glowed with the pigments of countless living cells, painting the waves in strange, shifting tones. Beneath the surface, the light faded quickly, trapped in the uppermost waters. The deeper layers dimmed into shadow, cut off from the rays that once reached them. The ocean's upper skin had become too rich, too crowded, too alive for its own balance to hold. As the days passed, the blooms spread farther out to sea. The water shimmered with gold and green at dawn, then darkened again as clouds rolled in from the heated horizon. Algae rose and fell with the tides, gathering in dense mats that rolled over one another in slow motion. When the blooms began to die, their remains sank in soft, heavy drifts. The ocean rained upon itself, a steady fall of microscopic bodies, each one carrying a trace of carbon from the sky above. What sank fed the darkness below. Bacteria flourished in this feast of decay, multiplying as they consumed the dead. But their hunger came at a cost. They used up the last traces of oxygen in the water, stripping it away faster than it could be replaced. Layer by layer, the deep turned breathless. The more life the surface produced, the less the depths could endure. The ocean was feeding itself into exhaustion. At night, the surface seemed alive with its own light. Waves broke in trails of pale blue sparks, the glow of plankton disturbed by motion. The sea shimmered under the stars as though it were burning from within. But this light was a fragile illusion, a last show of energy in a system growing unstable. Beneath the glow, the water was thickening with death. Fish that had once darted freely through the upper layers found their paths blocked by the density of the blooms. The water was too murky for sight, too warm for breath. Schools thinned, scattered, or disappeared entirely. Predators followed their prey into unfamiliar waters, chasing food that no longer gathered where it once had. The great filter feeders, whose mouths strained endless currents for sustenance, moved through waters rich in life but poor in nutrition. They found only emptiness beneath the color. The ocean had begun to smell faintly of sulfur and salt. It was a scent that hinted at what was hidden below, where decaying matter gathered faster than the water could carry it away. Gases formed in the still layers, whispering upward in bubbles that broke silently at the surface. Hydrogen sulfide rose in small breaths, a signal of rot, invisible to the eye, but unmistakable in its quiet persistence. The storms that circled the planet only stirred this restless mix further. Each gust churned the surface, dragging new nutrients upward from the shallows. Every storm became another catalyst, another push in the endless cycle. Warm winds gave way to thunder, lightning flashed across the horizon, and rain fell again into the same waters that had given rise to the clouds. Nothing in the ocean could rest. At times the sea cleared for a moment. The winds scattered the blooms, opening brief windows of blue that shimmered with deceptive calm. Sunlight slipped deeper, and for a short while the surface seemed to recover its stillness, but these moments never lasted. Within days, the green returned, swirling back together as if the water itself could not bear to be empty. Even far from the coasts, where the open ocean once shone dark and clear, the same transformation unfolded. Nutrients carried by currents ignited new blooms across the wide basins. The color of the sea changed everywhere. It was no longer the deep, endless blue of a balanced world, but the luminous, restless shade of something overfed. In these waters, oxygen dissolved less easily. The heat thickened the air-sea boundary, making it harder for life to breathe, even near the surface. Fish drifted upward, seeking fresher layers, their fins brushing the film of algae that now coated the waves. Crustaceans floated on their backs, their shells dusted with green powder. The sea had become crowded with motion, yet hollow at its core. From the coasts to the open ocean, the surface pulsed without pause. Each sunrise woke the blooms again. Each sunset left behind the slow descent of the dead. The cycle went on, unstoppable, tireless. It was a rhythm of creation and suffocation, of light feeding darkness. The ocean no longer slept. It turned in its fever, radiant and alive, burning quietly beneath the sun. The warmth that had crept across the planet was not content to linger at the edges. It pressed outward and upward, carrying moisture and energy into every corner of the atmosphere. The pattern of winds that once divided the world into distinct belts of climate began to shift. The great Hadley cells that shaped the tropics expanded, pushing the boundaries of the equatorial rains farther north and south. The deserts that had once marked the middle latitudes began to fade under the weight of water. The belts of dry air that circled the planet weakened, and the humid breath of the tropics seeped into the lands beyond. From the poles to the equator, vegetation advanced. What had begun as isolated forests along coasts and river valleys grew into an unbroken network of green, stretching across mountains, plains, and lowlands alike. It was not a single forest, but a collection of worlds, each adapted to the new rhythm of heat and water. In the equatorial regions, the canopies rose in layers so thick that sunlight barely reached the ground. The air shimmered with moisture, heavy with the scent of pollen and resin. Farther from the equator, rainforests gave way to dense subtropical woodlands, where broad-leaved trees mingled with early flowering plants that had found their moment in the warmth. Across continents, life rearranged itself. Plants that had once belonged to the tropics spread into regions that had never known such abundance. Species followed the rain. Palms, ferns, and magnolias advanced toward the poles, while new varieties of temperate flora pushed outward to claim the places left behind. The Earth's biomes were moving, as if the entire planet were exhaling and expanding at once. In the highlands, the forests climbed the slopes, where ice and tundra had once ruled. Valleys that had known only cold fog now filled with moisture-laden clouds rising from the lowlands. Rivers cut through these green corridors, swelling with the melt of what little snow remained. The water carried silt from the mountains into the floodplains below, spreading nutrients across entire continents. Every storm, every stream carried the ingredients of growth farther, seeding the earth with new life. The air itself had changed. It was richer in carbon dioxide than it had been for millions of years, and plants used it greedily. Photosynthesis reached its peak efficiency. Trees grew fast and tall, their trunks broad and their leaves thick with veins that pumped life through every cell. In only a few centuries, landscapes transformed beyond recognition. What had once been open scrubland became dense with vines and canopy. Grasses retreated to small clearings, crowded out by the surge of trees. Even the continent's interiors, once dry and wind-carved, grew damp and overrun with greenery. The tropical rain belts no longer obeyed their old limits. Monsoon systems strengthened, bringing heavy, rhythmic downpours to places that had once been arid. In some regions, the rains fell without pause for months. Elsewhere, the cycles alternated between flooding and sudden drought, each reshaping the land in its own way. The balance between air and earth, between wet and dry, was shifting faster than ecosystems could settle. Where the air rose thickest with moisture, forests became so dense that they created their own weather. Evaporation from the leaves fed the clouds above, which in turn released rain back onto the same ground. The cycle tightened, trapping humidity in vast, self-sustaining loops. Over time, these loops spread outward, merging until they covered most of the planet. The atmosphere was no longer divided cleanly by latitude. It had become a single, global engine of vapor and light. In this world, the soil was alive. The constant rain fed a cycle of growth and decay that never paused. Leaves fell and vanished into the ground, where fungi and bacteria consumed them, releasing their nutrients into the roots of new plants. The forest floor steamed with invisible heat from the endless work of decomposition. Everything fed something else. Every surface, from the bark of trees to the stones beneath them, became a platform for life. Yet not all regions shared the same rhythm. The interiors of the largest continents began to feel the tension between abundance and distance. While the coasts remained soaked, the far inland plains sometimes slipped into brief spells of dryness. Warm air rising from the forests carried moisture away, but the rains did not always return in equal measure. In these transitional zones, new ecosystems began to form. Woodlands alternated with grass-like vegetation that had learned to endure cycles of flood and drought. The boundaries between forests and open land shifted with every generation, never holding still. As the planet's climate zones migrated, so did the animals. Insects, small reptiles, and mammals followed the expanding forests. They adapted to the layered complexity of their new homes, feeding on the endless supply of leaves, fruits, and smaller creatures. Birds evolved to navigate the dense canopy, their wings shorter, their colors bright against the green light. Each species found a new place in the mosaic, shaped by the warmth that connected every corner of the world. The coasts mirrored this transformation. Where the tides met the land, mangroves thickened into intricate fortresses of roots that filtered water and anchored the soil. Swamps merged with forests, and forests stretched directly into the sea. In the shallow coastal zones, plants adapted to breathe in salt water, their roots catching silt and building new land grain by grain. Even the ocean fringes had become extensions of the great continental rainforests. Viewed from above, the Earth of this age would have appeared like a living emerald. The equatorial belt shimmered with deep green, the mid-latitudes gleamed with mixed canopies, and the polar regions, once bright white, had faded into darker hues of moss and forest. The world's map of climate had been redrawn, its old deserts and tundras replaced by an unbroken sweep of vegetation. The air was thicker, the storms stronger, and the circulation of moisture unending. It was a time when life had wrapped itself completely around the planet, a global web of forests that breathed in rhythm with the sky. The earth had become a greenhouse of its own making, every leaf and cloud part of the same vast pulse that carried warmth from one horizon to the next. And beneath that endless canopy, the planet's fever quietly deepened. For millions of years, the ocean had been the planet's great sculptor, shaping continents, feeding reefs, and binding the bones of its creatures with calcium drawn from stone. Every wave, every current, carried within it the ingredients of creation. When the balance between acidity and alkalinity was steady, the sea built its monuments in silence. Corals that rose like cities, plankton that bloomed and fell like snow, and shells that buried carbon in the deep. It was a cycle so old that even the rocks remembered it. But during this great warming, the balance began to tilt. The ocean did not roar or rage, it simply forgot how to build. The shift began quietly in the chemistry of the deep. As carbon filled the atmosphere, more of it slipped into the water, changing the equilibrium that governed calcium and carbonate. The line in the ocean where calcium carbonate could survive, known to scientists as the carbonate compensation depth, started to rise. For ages, that invisible boundary had lain far below the light, a place where shells and skeletons dissolved into dust. Now, it crept upward, year by year, swallowing the zones of life above it. The lysocline, where dissolution began, followed. It was as though the ocean's floors were lifting toward its surface, not in stone but in chemistry. Entire stretches of seafloor that had once been blanketed in white carbonate ooze began to darken. In sediment cores taken millions of years later, those layers appear as distinct black or brown bands, the record of a world where the ocean's foundations thinned. The once bright plains of the deep sea, built from the rain of dead plankton and coral fragments, gave way to clay and iron-stained mud. The effect rippled upward. Coral reefs, those slow-growing fortresses of calcium, began to falter first. Their polyps could still draw minerals from the water, but only with greater effort. The balance between building and dissolving reversed. Where the waves once struck living rock, they now struck the bare skeletons of reefs stripped of life. In shallow tropical seas, whole structures that had taken millennia to form began to crumble within centuries. Bright colonies dulled to a pale stone, their intricate forms softened by the constant wear of water that no longer gave as much as it took. In open waters, the changes were subtler but more profound. The tiny foraminifera and coccolithophores that built their shells from calcium carbonate began to fail. The saturation horizon had moved above them, and the water that had once protected their skeletons now wore them down even as they lived. The shells that did form were thinner, more fragile, their patterns incomplete. When they died, many never reached the seafloor intact. They dissolved mid-descent, their remains scattered into ions that disappeared into the water column. Over time, the deep ocean's chalky snow slowed. The steady rain of carbonate that had covered the abyss for millions of years was replaced by a dull, sparse fall of organic matter. The sediments that did reach the bottom were darker, poorer in calcium, and richer in clays and iron. The ocean's ability to bury carbon, its slow breathing mechanism, was weakening. Each grain that failed to settle was a fraction of carbon left to circulate, a molecule that would remain part of the planet's fever. Not all organisms suffered equally. Those that built with aragonite, the more soluble form of calcium carbonate, were hit hardest. Many corals, pteropods, and certain shellfish vanished from large parts of the ocean. Calcite builders, whose structures were slightly more stable, persisted longer but grew fragile, their layers thin as eggshells. Reefs in some regions adapted by shifting composition, dominated by sponges and soft corals that did not rely on calcium at all. In a few sheltered basins, limestone platforms continued to grow, but they did so slowly, their edges marked by zones of partial dissolution. The ocean had become selective in its generosity. The rising carbonate compensation depth left its signature in every basin. In some regions, the CCD shoaled by hundreds of meters, erasing entire carbonate platforms that had existed for tens of millions of years. Continental margins that had once been factories of limestone sedimentation became barren plains of silty clay. In others, the shoaling halted just above the shelf, allowing some shallow water environments to survive. The map of calcium stability had been redrawn, a patchwork of survival and loss. As the ocean continued to warm, the chemistry of the seafloor evolved in response. Iron minerals, once buried, oxidized and stained the sediment red and orange. Hydrogen sulfide, produced by bacterial decay in oxygen-poor waters, left streaks of black through the layers. The carbonate, that once locked carbon into solid form, now lingered in solution, drifting between molecules of water, waiting for a future equilibrium that would take hundreds of thousands of years to return. Recovery, when it began, would not be quick. The ocean's calcium cycle is one of its slowest rhythms. To rebuild its lost stores, rivers would need to carry fresh minerals from eroded mountains back to the sea. Rain would have to dissolve rock, atom by atom, feeding calcium back into the water until the balance tipped once again toward creation. That process would take hundreds of millennia, far longer than the lifetime of any single species that had suffered from the loss. Beneath the surface, the transformation continued in silence. The corals that managed to survive grew in twisted, stunted shapes, their skeletons soft to the touch. The sands that once gleamed white on tropical shelves turned gray. Whole coastlines changed color as the sediments beneath them shifted from carbonate to clay. The bones of the ocean were softening. If one could have drifted through those waters then, the change would not have appeared violent. The waves still broke, the light still shimmered, but beneath that calm, the chemistry of life itself was being rewritten. Each shell that dissolved left behind a trace of calcium and carbon that would one day find its way into the air again. The sea had become an archive of its own undoing, recording in every layer the quiet collapse of its ability to create stone. The ocean still moved, still carried heat and life across its surface, yet within it, something fundamental had shifted. It was no longer the planet's builder but its dissolver, slowly erasing the monuments it had made. What had once been a cradle of creation had become a vessel of forgetting, where calcium, carbon, and time dissolved together into the deep. The air had changed. It was no longer clear and blue, no longer crisp or light. The heat that had built for centuries began to rise from the land itself, lifting particles of dust, ash, and vapor into the sky. The atmosphere thickened, folding layers of color between the sun and the earth. When light passed through, it no longer came out white and pure. It emerged transformed, filtered by the haze that blanketed the world. The days began to glow in a soft golden light. The sun seemed larger, yet somehow distant, its brilliance muted by the weight of the sky. From the ground, it looked as if the planet had drawn a veil across its face, a thin shimmer that bent the light into shades of copper and amber. The air shimmered with warmth, and shadows turned long and soft, fading into one another until distance lost its sharpness. Every morning began with a slow rising of color. The horizon blushed not with pinks or oranges, but with a dull metallic hue. The sun's edge trembled as it broke through the haze, its rays scattering through the fine dust that now filled the air. What should have been bright daylight became something gentler, as though the world had slipped into an eternal afternoon. The forests that had once thrived under strong sunlight now found themselves under a dim canopy of gold. The leaves absorbed what light they could, their surfaces glistening with moisture in the heavy air. But the strength of the sun was weakened. The plants that relied on its energy began to slow their work. Photosynthesis, the quiet process that turned sunlight into life, faltered in the gloom. Growth slowed. The forests, already thick and restless, seemed to pause. The air itself carried the taste of minerals, a faint metallic tang that drifted through the wind. Tiny particles of iron and sulfur, lifted from the dry earth and the churning seas, danced in the sunlight, catching and bending it in ways that turned the sky into a living mirror. The blue that once defined the atmosphere faded away, replaced by this strange, endless glow. From space, the earth would have seemed cloaked in bronze, its clouds tinted with gold. At noon, the light was brightest, but still diffused. The heat was not a sharp burn, but a constant presence, wrapping everything in warmth. The ground radiated it upward, feeding the haze that made the world shimmer. Even the rain, when it came, fell tinted, as though it carried some of the sky within it. Droplets gathered the color of the air, soft and golden as they fell upon the green below. Animals that had adapted to the thick forests and humid air began to sense the change. The days no longer felt distinct from the evenings. Shadows lengthened sooner, and nights arrived slowly, blending into the haze of the day. Some species began to shift their rhythms. Insects flew later into the dim light. Small mammals moved cautiously through the glow, their eyes adjusted to the half-light that never truly left. In the oceans, the change in light reached down through the surface. The plankton that floated near the top found their world darker than before. Their photosynthetic cells worked more slowly, producing less of the energy that fed the marine food chain. The golden glow that bathed the waves was beautiful from above, but beneath it, the waters grew quieter, less alive. The balance of light and life had tilted once again. Dust storms swept across the continents more often now. The soil, dry and loose after long cycles of rain and heat, lifted easily into the wind. Fine grains drifted for thousands of miles, carried across oceans, settling on distant lands and waters. Each storm added a new layer to the haze, thickening the veil that dimmed the sun. In the evenings, when the sun sank low, the world turned to copper. The horizon deepened to burnt orange, and the light fell heavy upon the trees and rocks, making them seem carved from metal. The atmosphere glowed long after the sun disappeared, holding on to the light like a memory. The nights were darker but not cold. Heat clung to the air, refusing to fade. The stars, once bright and sharp, were now faint behind the curtain of haze. Only the largest ones could pierce through, flickering like distant sparks. The moon rose dull and red, its reflection colored by the same suspended particles that tinted the days. The cycles of night and day had lost their clarity. The world existed in a constant, lingering glow. Every surface reflected the change. Rivers gleamed like melted brass. The leaves of plants took on a faint metallic sheen, as though trying to mirror the sky. Even the air above the mountains seemed solid, a slow-moving golden fog that never cleared. The planet had entered a strange kind of stillness, not the silence of emptiness, but the hush that comes when everything holds its breath at once. The air, the light, and the land existed in fragile equilibrium. The sun's warmth, once the giver of life, now carried a weight that pressed on everything below. The sky no longer simply illuminated the world, it became part of it, dense with the same energy that had driven the fever forward. The color of the world had changed. It was no longer the bright blue and green of a healthy earth. It was something ancient, as if the planet had slipped into a memory of its own creation when dust and light first mingled in the birth of the world. The sky had turned to copper, and beneath its glow, the earth continued to breathe, slow and heavy, under the weight of its own heat. The world had grown restless. Heat shimmered through the air, and the forests that once drank endlessly from the sky had reached their limit. The rains still came, heavy and frequent, but the warmth that followed dried the ground faster than the water could sink. Beneath the canopies, the soil baked into cracked mosaics of clay. Fallen leaves curled at the edges, brittle and thin. The air that drifted through the trees was no longer cool and damp. It was thick, warm, and charged with something waiting to ignite. Across the continents, lightning became more common. The storms that gathered above the steaming forests were vast and powerful, their clouds swelling into towers of gray and copper. The energy of the overheated atmosphere fed them. When they broke, they did so with violent grace. Forks of lightning streaked across the sky, splitting the air into blinding threads. Most strikes found only rain, but some found what they needed: the dry undergrowth, the fallen wood, the exposed bark of trees that had cracked under heat. Even the wettest forests, those that had survived under constant downpour, began to burn. At first, the fires crept low and slow, moving across the forest floor like a living shadow. They consumed the litter of leaves and branches, smoldering rather than roaring. But when the heat grew and the winds carried sparks to the upper canopy, the fires lifted. They climbed the vines, leapt between treetops, and turned green crowns into pillars of flame. The sound of rain was replaced by the hiss and crackle of combustion. The smoke did not rise quickly. It clung to the air, drifting between trunks and branches, wrapping the forest in a veil of gray. The light that filtered through the haze turned the world amber. Ash fell in slow motion, soft as snow. For days, the fires burned without rest, then weakened, leaving behind fields of blackened stems and embers that glowed faintly in the dark. The fires did not come once and vanish. They became part of the world's rhythm. In some places, the trees adapted. Certain species grew thicker bark, resisting the flames that licked at their bases. Others released seeds only when exposed to fire, taking advantage of the clearings left behind. The forests, as though aware of their own mortality, learned to reset themselves through burning. But each new growth was smaller, thinner, less lush than before. The world's green lungs were breathing in short, uneven gasps, the atmosphere filled with smoke for years at a time. From above, the planet's colors shifted once again. The blue of the ocean and the green of the forests were muted beneath a veil of brown haze. Dust and soot circled the globe, mixing with the copper sky, softening the sunlight until the days seemed trapped in a permanent dusk. Animals fled before the advancing flames. Those that could fly took to the smoke-filled air, searching for untouched ground. Those that could not ran, their movements guided by instinct more than understanding. Many found safety in rivers and wetlands where the flames could not follow. Others succumbed to exhaustion, lost in the vast stretches of smoke and heat. The soil beneath the burned forests turned black, rich with carbon. In time, new plants sprouted from it, fragile and pale at first, then stronger as rain returned. Moss crept over charred logs, ferns unfurled from the ashes, trees grew again, but the pattern of life had changed. Fire had rewritten the cycle of renewal. Each blaze released carbon that had been locked away in the forests for centuries. The air, already burdened with warmth, grew heavier still. The fires fed the fever, and the fever fed the fires. The two became inseparable, each sustaining the other in a quiet exchange that spanned thousands of years. Even after the flames passed, the evidence remained. Layers of charcoal built up in the soil, black streaks marking each generation of fire. These layers would endure long after the forests themselves vanished, buried beneath new sediments, preserved as whispers of a world that had learned to burn. Lightning storms continued to roll across the sky, their light flickering through the smoke. They struck the same valleys and plains again and again, igniting what little remained of the old forests. Some fires burned hot enough to melt the soil into glassy shards. Others moved gently, clearing only the surface before dying in the rain. In the higher latitudes, where the air once carried frost, the fires came too. The forests that had grown along the edges of the Arctic, strange jungles of birch and palm, burned under the midnight sun. The reflection of the flames shimmered across pools of water where ice had once lain. Even at the poles, the planet had no refuge from the heat. The fires changed the scent of the world. The air carried traces of resin, charcoal, and earth. Rain, when it fell through the haze, came down tinted and acidic, washing soot into rivers and lakes. The water turned dark, and the nutrients from the ashes spurred new bursts of growth along its banks. Life adapted again, as it always had, but each adaptation was a step further from what the earth had once been. The forests continued this cycle for thousands of years. Growth, fire, ash, regrowth, each phase shorter than the last. The trees became smaller, their canopies thinner. The air shimmered with heat even in the shadows. It was a planet still alive, but constantly remaking itself through destruction. Somewhere beneath the ash, the memory of green still waited. The seeds that survived in the soil held the promise of new forests, even as the old ones turned to smoke. The fires came and went with the storms, their glow rising and fading like the pulse of the earth itself. The world burned not in rage, but in rhythm, as if the fever had found its own heartbeat. The rise that had seemed endless finally began to slow. The great fever of the earth did not break, but it stopped climbing. The warmth leveled off and entered a long plateau. Full recovery of ocean chemistry and global climate patterns took on the order of 100,000 years or more. The change was so gradual that no single lifetime could have sensed it, yet across millennia, the planet's restless pulse began to ease. The air was still thick with carbon, the seas still heavy with heat, but the pace of transformation had weakened. The world moved differently now. The sky hung low with haze, and the light that filtered through it glowed amber and soft. Winds no longer screamed across the continents as they once had. The storms continued, but their fury came and went in rhythms that no longer built or broke. It was as if the planet, after so long in motion, had taken a breath and held it. Across the continents, this stillness unfolded slowly. The forests that had once burned and regrown in frantic succession began to settle. Their trees, smaller and darker than before, grew in thin, scattered stands. The leaves were thick and waxy, shaped to endure constant moisture and heat. In the soil beneath them, New roots tangled through ash and mineral, binding what centuries of floods had loosened. Life was returning, but it grew cautiously, as though uncertain of the ground it stood on. Rivers wound through plains that had been reshaped by storms. Their courses wandered like threads through new valleys and shallow lakes. The water was heavy with sediment, colored red and brown from the iron-rich soil. Where the floods had once torn through forests, slow swamps now formed, steaming beneath the thick air. The world no longer rushed forward, it simply remained. In the oceans, the change was deeper and quieter. The upper waters shimmered with warmth, bright with drifting plankton that had survived the long crisis. Below them, the darkness still waited. Circulation had weakened so completely that the deep ocean barely stirred. The abyss remained starved of oxygen, its silence unbroken. Yet in the shallows, small lives began to multiply again. Tiny plankton spun through sunlight, fragile but persistent. Each new cell that captured light was a small act of endurance, a sign that balance, though distant, was still possible. Over that long pause, slow earth processes, rock weathering, sediment burial, and changes in ocean circulation quietly began to pull the planet back toward balance. Rain fell warm and mineral rich, washing over stone that had once baked in volcanic heat. Silicate rocks began to dissolve, drawing carbon from the air one molecule at a time. The runoff carried this captured carbon to the sea, where it sank into sediment and vanished from the atmosphere. It was chemistry moving at the pace of continents, a slow dialogue between sky and stone. The temperature remained high enough that no ice returned to the poles. The world stayed green and damp, its equators steaming, its poles wrapped in rain and forest. Days were long and hazy, and the nights glowed faintly with trapped heat. Across that humid planet, the cycle of water ruled everything. Clouds formed endlessly, their weight pressing on the air, and every storm fed rivers that wandered between new deltas and ancient shores. On land, creatures adapted to this unchanging warmth. Mammals stayed small, nimble, their hearts beating fast in the heavy air. They climbed, burrowed, and swam through a landscape thick with vegetation. Insects thrived, their wings flashing gold and green in the filtered light. Birds filled the trees, their feathers glistening with the damp. Each creature carried in its body the quiet mark of endurance, shaped by the world's long fever. In the sea, the sediments began to change color. The black, sulfur-rich layers that had once marked suffocation gave way to pale mud, then to faint traces of calcium. The ocean was slowly regaining its ability to build again. Microscopic shell builders returned, tentative at first, their skeletons fragile and thin. Yet they endured, forming the first bright flecks in the layers of the deep. Each tiny shell that survived added to the slow climb toward stability, a whisper of recovery written in stone. The air above was calmer now, dust no longer choked the light, and the skies had begun to clear. The sun shone through the haze in muted gold, scattering across the surface of warm seas. The planet looked peaceful from afar, but within, its systems moved with careful precision, as if relearning a forgotten rhythm. Every raindrop that touched the soil carried away a trace of the carbon that had once set the world ablaze. Every buried shell, every grain of dissolving rock was part of the long repair. Time in this age passed differently. Centuries were moments. Millennia were the measure of breath. Forests rose and fell in the span of what felt like days to the earth itself. The rivers changed their paths again and again, cutting new lines across plains that had once been ocean floors. Mountain ranges, softened by constant rain, eroded grain by grain into the valleys below. The warmth lingered, patient and steady. Nothing rushed. The planet had not yet healed, but the fever had stopped spreading. The sea remained heavy with carbon, the land dark with moisture, yet life continued its slow climb through the stillness. It was not recovery in the way of renewal, but balance in the form of endurance. For tens of thousands of years, the earth hovered there, suspended between what it had been and what it would become. Its air was thick, its seas restless, but the great ascent had ended. The world was learning to hold its warmth without collapsing under it. It was a pause, not of peace, but of breath, the moment between suffering and restoration when time itself seemed to wait before moving forward again. The planet healed not by miracles, but by chemistry and erosion. Rain and rivers carried dissolved rock into the sea, and silicate weathering chemically bound carbon and removed it from the air. What followed was not a dramatic recovery, but the quietest kind of repair, so gradual that no creature could have noticed it unfolding. It began with rain, endless and patient, falling on a world still warm from its long fever. Each drop held a trace of the sky within it. As the rain touched the land, it began to eat gently at the stone, carving away the surface, carrying fragments of mineral toward the sea. The reaction between water, carbon, and silicate rock worked in silence, pulling carbon dioxide from the air and locking it within new compounds. It was the slow chemistry of redemption, repeated across mountains and valleys, grain by grain, storm by storm. Mountains wore down under the weight of time. The sharp ridges softened, the slopes blurred, as rivers dragged their dissolved cargo toward the coast. Over thousands to tens of thousands of years, three slow processes helped. Rock weathering locked carbon into solution, ocean burial trapped organic matter in sediments, and carbonate chemistry gradually rebalanced as plankton returned. Together, these forces reshaped the surface of the world and the air above it. The atmosphere, once thick with greenhouse gases, began to ease. The heat that had lingered so long started to drift outward into space, faintly, imperceptibly. The oceans were the first to show signs of this turning point. For so long they had been heavy with acid and warmth, but now their chemistry began to change. Rivers carried dissolved silicate and calcium from the land, and the water slowly turned less corrosive. The sea regained its ability to hold life. The process was delicate, fragile even, but it was relentless. The ocean that had once dissolved shells was beginning to make them again. The first to return were the plankton. They floated near the surface, capturing sunlight and weaving it into the fabric of life once more. Their tiny shells, made of calcium carbonate, began to drift down after death, forming the faintest dusting across the seafloor. These microscopic builders turned chemistry into motion, drawing carbon from the sky and burying it grain by grain. The ocean's breathing, its cycle of absorption and release, had begun to steady itself again. The color of the sea changed slowly. The milky green haze of decay faded, replaced by deeper blues and soft emerald shallows. Sunlight could once again reach through the water, illuminating the drifting plankton and the small creatures that followed them. Over generations, coral polyps began to grow again in the shallows, fragile at first, then stronger as the chemistry allowed. Around their stony branches, small fish returned to feed. Crustaceans crawled along the growing reefs. Each new shape of life added strength to the recovering web. On land, the changes took even longer. The soil that had been washed away by storms began to form again, fed by decaying plants and fungal threads that worked their way through the damp ground. Forests spread where fire had once swept. The trees grew differently than before, smaller perhaps, but steady. Their roots gripped the new soil and slowed the floods. Their leaves drew in carbon with every breath of light, joining the slow, patient labor of healing. The air thinned with time, the haze began to fade, and the sky regained its color. What had once glowed gold and copper in the heat now shifted back to pale blue. The sunlight lost its heaviness, and the winds turned cooler. Clouds moved more freely, and rain began to fall in gentler rhythms. Each cycle of evaporation and rainfall carried away another trace of carbon, another measure of the old fever. Beneath the continents, deep within the crust, the work continued. The minerals formed from the weathering of stone were carried into the ocean, where they sank and hardened into rock. Layer upon layer of limestone and shale buried the memory of the great warming. The carbon that had once filled the sky was now trapped in solid form, stored away for millions of years in the planet's bedrock. Even as the Earth cooled, its recovery never stopped. New species rose where others had vanished. Mammals grew stronger and more varied, their bodies adapted to the stable warmth that still lingered. Forests spread farther across the continents, and rivers carved new deltas where the land met the sea. The balance between air, land, and water was not perfect, but it was whole again. As the chemistry eased, life could reestablish more complex food webs. Plankton, fish, and forests reappeared in rhythms that matched the returning balance of carbon and oxygen. The oceans exhaled what they could, the continents drew in what remained, and the planet settled into its slow, living equilibrium. No single moment marked the end of the recovery. It simply continued, quietly, over tens of thousands of years. The rocks breathed, the rivers carried, and the seas received. From these motions came renewal. The earth did not heal quickly, but it healed completely by the patient labor of water, stone, and time. When the fever finally eased and the air grew light again, the world that remained was unfamiliar. The forests that stretched across the continents were quieter, their canopies thinner, and their colors muted beneath the still warm sky. The oceans had softened, no longer acid and violent, though they still shimmered with traces of what had been lost. Across the planet, the silence of recovery hung heavy, and within it, life began its careful return. The creatures that had endured through the heat were few, and they were small. The great reptiles that had once ruled the world were long gone, and the mammals that had survived were not the large, fur-covered beings that would one day walk the earth. They were small, quick, and delicate, their lives measured in days and seasons rather than centuries. These tiny survivors, no larger than a hand, inherited a world that had been remade. In the undergrowth, early primates moved quietly through the branches. They were nimble, with grasping fingers and wide, curious eyes. They had learned to live where the world was still soft, feeding on fruits and insects, darting through the thin trees that grew in the humid forests. Each movement was cautious, each breath taken in a world that was still learning to balance itself again. Nearby, small horses no larger than a fox trotted through ferns and low plants. Their hooves had not yet hardened into the shapes we know today. Instead, their feet were spread wide to walk on soft, muddy ground. They fed on tender shoots and leaves, nibbling through the new greenery that blanketed the recovering earth. In this warmth, size was a burden. Smaller creatures released heat faster, and that made survival possible. Evolution favored the light-footed, the quick, and the clever. Rodents scurried across the forest floor, burrowing into soft soil where the roots of new trees held the ground together. They were the quiet architects of this new age, their tunnels turning the soil, their hoarded seeds helping forests spread. As they dug and nested, they became part of the slow rebuilding that reshaped the planet after so much loss. Every handful of earth they moved became part of the Great Repair. The skies were not empty. Small birds, descendants of dinosaurs that had survived the long darkness after the last great extinction, filled the air with the first tentative songs heard in millennia. Their feathers were dull at first, colors muted by the haze that still lingered in the sky, but in time, their plumage brightened. Their wings carried seeds between continents, scattering life across oceans and valleys. In the rivers, early forms of modern fish found new homes. The water had cleared, its chemistry softened, and the ancient oxygen-starved depths began to breathe again. The food chains rebuilt themselves from the smallest links upward. Plankton fed tiny crustaceans, which fed small fish, which in turn fed the birds and mammals that hunted along the shores. Life was growing in layers again, connected once more in a fragile but strengthening web. The earth itself seemed gentler. The storms that once scoured the continents now came with softer edges. The rain was clean again, washing through the soil and filling lakes that glimmered with new clarity. The scent of living things filled the air, the musk of animals, the sweetness of flowers, the earthy breath of wet ground. The world that had once burned now exhaled life. In this new calm, evolution moved quickly. The heat had left behind not only scars, but opportunity. With so many species gone, the survivors faced an open planet, filled with empty niches waiting to be filled. Tiny creatures began to diversify. Some adapted to climb, some to dig, some to swim. The mammals that had once hidden in the shadows of larger predators were now free to explore, to expand, to experiment with form and behavior. Each generation changed a little more than the last. Teeth reshaped for new diets, limbs grew stronger for climbing or running, senses sharpened to meet new challenges. The world was still warm, but it was stable enough for life to test itself again. And every small success left an imprint, a new path for others to follow. Insects thrived in the warmth, buzzing through the forests in bright clouds. They pollinated the flowering plants that had evolved to take advantage of the new climate. Together, they formed one of the most enduring partnerships in the history of life. The scent of blooming flowers became a signal, and the hum of insects became the rhythm of the recovering world. Even in the polar regions, where once there had been ice, life returned. The Arctic and Antarctic remained free of glaciers, covered instead by forests of birch and pine, their branches heavy with moss. Small mammals made burrows there too, feeding on leaves and shoots during the long summer days. In these high latitudes, the sun still lingered on the horizon, casting endless twilight over the green that had replaced white. The earth was still reshaping itself. The continents drifted slowly, moving along the molten currents below. Mountains rose where old seas had once spread. Rivers carved new valleys through soft stone. With each shift, ecosystems adjusted, and the animals moved with them, following the warmth, the water, and the food. The world that had nearly ended was now alive again, though it was quieter and smaller than before. In that quiet, the foundations of the modern world were being laid. The small mammals that crept and climbed, that hid and searched and survived, would one day give rise to entire lineages of new life. They did not know that they carried the future within them, that from their tiny forms would emerge the ancestors of elephants, whales, and humans. For now, they lived in the moment the planet had granted them. The forests rustled softly, the rivers flowed clear, and the air shimmered with the warmth of a sun that was no longer angry. The age of giants had ended, and in its place had come something gentler. It was the age of small survivors, of beginnings so quiet that only the earth itself could feel their significance. Beneath every continent, beneath the ocean basins and mountain roots, lies the memory of a planet that once burned with warmth. It is written not in language, but in layers. Every grain of sediment, every shell, every trapped bubble of air is a word in the story of Earth's fever. For 56 million years, this story has waited, pressed beneath time, until we learned how to read it. The record begins in the deep sea, in sediments laid down one particle at a time. For countless ages, the shells of tiny planktonic foraminifera and coccolithophores drifted downward after death, settling gently onto the ocean floor. Each carried within it a trace of the world it had lived in: the temperature of the water, the balance of carbon, the chemistry of the air above. Layer upon layer, these shells created a slow snowfall of calcium, forming a continuous chronicle of life and change. When modern science began to drill deep into the ocean basins, long cores of sediment were brought to light. They looked, at first glance, like cylinders of mud and stone, but inside them lay a record that stretched back tens of millions of years. Each centimeter represented centuries of history. Within those cores, scientists discovered a thin, unmistakable layer, a dark band separating the ordinary world from something extraordinary. Above and below it, the sediments were pale, filled with the chalky remains of marine life. But at that narrow boundary, the color shifted sharply to a reddish brown, rich with iron and organic carbon. It was the fingerprint of a world transformed. The fossils within that band tell the story with precision. Foraminifera, once abundant across the seafloor, suddenly grew smaller, thinner, and then vanished entirely. Many species never returned. Their shells, once bright with calcite, were dissolved by water that had grown too corrosive to preserve them. The sediments that had been white with carbonate turned darker, stained by iron, released when the deep ocean lost its oxygen. To the trained eye, those colors are more than stains, they are the chemical scars of suffocation. Deeper within the same layers lies the evidence written in carbon itself. Every atom of carbon comes in slightly different forms, called isotopes. When the planet's balance shifts, so do their proportions. During the Paleocene-Eocene Thermal Maximum, those isotopes changed abruptly. Across cores taken from every ocean and continent, the ratio of heavy to light carbon drops in a single, global heartbeat. That plunge, called the carbon isotope excursion, reveals an immense injection of light carbon into the atmosphere. Carbon likely released from methane hydrates, volcanic intrusions, or massive fires that burned across continents. The tilt in those isotopes is the chemical echo of a planet overwhelmed by its own breath. Above that dark line, the recovery begins, slow and uneven. The isotopes climb gradually toward their former balance, but the shells of foraminifera remain rare and fragile for hundreds of thousands of years. Even when life returned, it bore the memory of collapse. The chemistry of the deep sea continued to carry that imbalance long after the skies had cooled. On land, the evidence takes a different form. Ancient soils from North America, Europe, and Asia hold pollen and leaf impressions that trace the migration of forests. Grains of pollen from palms and magnolias appear where once there had been temperate trees. Farther north, sediments record the arrival of species adapted to heat and rain, proof that entire ecosystems had moved toward the poles. Each grain of pollen is a map of climate rewritten. Within the same layers lie charcoal fragments, fine as ash, the remnants of ancient fire. Under microscopes, they glitter like black glass. Their presence in great abundance reveals a landscape that burned often and widely. During the peak of warming, the atmosphere's high oxygen and carbon levels turned vegetation into fuel. The fires would have swept across the continents, clearing forests and releasing yet more carbon to the air. Charcoal is the fossil of that destruction, a quiet record of flame. The rocks also remember the silence of the deep. In cores taken from abyssal plains, layers once bright with carbonate ooze are interrupted by clays streaked with sulfur. These are the sediments of a dying ocean where oxygen vanished and bacterial chemistry took over. The sulfur isotopes in those layers shift alongside the carbon record, showing that the oceans were not only warmer, but changed in their very breath. It is in these same sediments that the benthic foraminifera crash appears the abrupt disappearance of deep-sea species that could no longer survive without oxygen. Even the fossils of land animals record the event in their bones. The teeth of early mammals, found in the ancient floodplains of Wyoming and Europe, reveal that bodies had grown smaller during the heat. Their proportions shifted in only a few thousand years, evolution recorded in centimeters rather than epochs. The isotopes locked inside their enamel mirror those in the ocean sediments, tying the fate of land and sea together in the same chemical pulse. Each type of evidence speaks to a different consequence, and together they form a single mosaic of change. The carbon isotopes mark the breadth of the atmosphere. The iron-stained seafloor records the loss of oxygen. The vanished shells mark the retreat of calcium from the water. The pollen maps the forest's long march toward the poles. The charcoal captures the rhythm of fire that followed. None of these clues stands alone. Each is a verse in the same story of imbalance and adaptation. Today, those cores and fossils rest in quiet archives, stored in rooms kept at constant temperature and dim light. Rows of labeled cylinders line the walls, each holding a piece of deep time. Under microscopes, the remaining shells glimmer faintly, their patterns unchanged since the day they sank. To look at them is to see the handwriting of the planet itself, delicate, deliberate, and enduring. The rock does not exaggerate, it does not invent, it only remembers. Within its thin layers lie the signatures of a world that warmed, gasped, and slowly healed. And though the seas have long since cooled and the forests shifted again, the record remains intact, waiting patiently for us to read it. The story of the Paleocene-Eocene Thermal Maximum was not discovered in a single place or in a single moment. It emerged slowly, like the world itself revealing a secret it had buried deep within. Cores drilled from ancient seabeds, from the North Atlantic to the South Pacific, told the same tale. Each layer of sediment was a memory, pressed flat by time. And within those layers, scientists began to see a pattern, one that spoke of warmth, imbalance, and recovery that came only after ages of struggle. The clues rested in the mud, in the colors that shifted from pale to dark, in the tiny shells that grew thinner and fewer as the layers climbed. The changes were unmistakable, even to the naked eye. The deeper layers told of stability, of a world that had found balance for millions of years. Then came the thin band of carbon, rich and dark, where everything shifted. The chemistry changed, the shells vanished, and the signs of heat spread across the geological record like a fever that had swept the entire planet. For decades, scientists puzzled over what could have caused such a spike. The evidence pointed to carbon, immense amounts of it, released in a short burst of time. It was too much for the planet to absorb. The ocean had taken in what it could, and the land had responded in kind, but the balance had broken. The air had grown heavy with greenhouse gases, and the world had warmed by at least 5 degrees Celsius in what was, geologically speaking, an instant. The timing was the key. It was not only how much carbon was released, but how fast. The rocks showed that when the change came suddenly, life could not adjust in step. Deep sea creatures vanished almost entirely, leaving behind empty layers of sediment where shells should have been. Forests migrated toward the poles, but many species that could not move fast enough disappeared. Mammals shrank in size to survive the heat. Evolution, which usually unfolded over millions of years, was forced to accelerate, reshaping life in tens of thousands. From these buried records, scientists learned that the Earth is both resilient and fragile. It can heal itself, but only across spans of time so vast that no living thing could measure them. The chemical weathering of rocks that slowly drew carbon from the sky took more than 100,000 years to bring the world back into balance. To the planet, that was recovery. To life, it was survival through endless generations of change. When researchers examined the carbon isotope data from the PETM, they found something haunting. The fingerprints of that ancient warming matched those of today. The same sharp decline in carbon ratios that once marked the onset of the fever now appears again in the layers of the modern world. But there is one difference, and it is the most important one of all: the speed. During the Paleocene-Eocene warming, the carbon had flooded into the atmosphere gradually, even at its fastest. Now, the same amount of carbon that once took thousands of years to release is being added to the air in less than 200. The isotopic signals that once stretched across layers of rock now fit within a single human lifetime. The planet's chemistry is changing again, but this time it is happening at a pace that even geology struggles to capture. Scientists compare the records of the past with measurements taken from the modern ocean. The patterns align almost perfectly. The surface waters are warming, and the pH of the sea is falling, mirroring what once happened during the PETM. Tiny plankton that build their shells from calcium carbonate face the same struggle their ancestors did 56 million years ago. Coral reefs bleach and crumble in ways that echo the old fossil scars found in cores. The deep ocean, again, is beginning to lose its oxygen. But unlike in the ancient past, this change is being watched unfold in real time. The lessons of the old Earth are now instruments of warning. By reading the rocks, scientists have learned that ecosystems can adapt, but only if change comes slowly enough for evolution to keep pace. When it comes too fast, the chains of life break before new ones can form. In laboratories around the world, researchers handle the fragments of that buried age with care. They examine the isotopes, the shells, and the minerals, using them as guides to understand what lies ahead. Every sample tells a story of cause and effect, of thresholds crossed and balances lost. They see that the Earth, though vast, has limits to its stability. When too much carbon enters the system too quickly, the feedbacks that once kept it steady can no longer hold. The rock cores from the ancient oceans have become mirrors of the present. Each one reflects what is already beginning to unfold: warmer seas, shifting rains, and species on the move once more. The past offers no prophecy, only patterns, but those patterns are enough to remind us that the laws of chemistry have not changed, nor have the timescales of the Earth's repair. The PETM stands now as both memory and map. It shows that the planet can recover from immense disturbance, but not without loss, and never quickly. The creatures that lived through it left behind the evidence in their bones, in the shells that turned to stone, and in the chemical breath of the air they once inhaled. From them, scientists have learned that life continues, even when the world turns strange, but that every degree of warmth comes with a price written in time. And so, the story that began in mud and stone continues to echo. The same signals that whispered through ancient sediments are now rising again, carried by our own age of change. The Earth, as it did before, will adapt. The question is not whether it can, but how much of what we know will endure long enough to see it do so again. In the deep record of the Earth, time is not measured by days or years, but by the slow settling of sediments, the faint shift of isotopes, and the rise and fall of carbon through air and sea. Across those layers, the story of every warming and cooling, every breath of the planet, is written in the chemistry of stone. Among these rhythms, one moment stands apart: the great warming of 56 million years ago, the Paleocene Eocene Thermal Maximum. It was an event of immense change, yet even then, the world turned slowly. Carbon moved through its cycles like a steady tide. During that ancient transformation, carbon entered the air at a rate scientists estimate to have been only a fraction of a petagram each year, perhaps 1/10 or even 1/20th of what we release now. A petagram is 1 billion metric tons, a number so large it almost escapes comprehension. The ancient pulse unfolded across tens of thousands of years, giving oceans and ecosystems time to absorb, adapt, and reorganize, even as they strained under the pressure. Today, the rhythm has changed. The modern world now adds roughly 10 petagrams of carbon to the atmosphere every single year. The scale of release may be similar in total 3 to 5 trillion tons of carbon during the entire ancient event, and nearly as much already from human activity, but the tempo is utterly different. What once unfolded over 20,000 years is now compressed into barely 200. The difference is not merely in magnitude, but in speed and in climate. Speed is everything. The rocks that carry the memory of the PETM show this clearly. Their isotopic signatures reveal the same fingerprint of light carbon now rising in the air, the mark of material once locked in life or in ancient deposits. But in those stones, the change stretches across centimeters of sediment, each layer representing centuries. In our time, the same shift has occurred in the span of a single human lifetime. The line that once blurred across deep time has become a spike. In the ancient world, the release came from within the earth itself. Lava from volcanic intrusions met layers of organic matter, turning rock into gas. Methane hydrates, long trapped beneath cold seafloors, thawed and seeped upward in quiet plumes. Forests burned and regrew, balancing one wave of emissions with another. The process was vast, but the pace allowed natural systems to respond. Weathering of rocks slowly drew carbon back from the air. Rivers carried dissolved minerals to the sea, and plankton captured the excess in fragile shells that drifted downward into the deep. The planet could still keep time with itself. Now, the source of change is no longer volcanic or tectonic, but mechanical and constant. Engines, furnaces, and factories release carbon as fast as the fuels beneath them allow. The flow no longer depends on the pace of magma or the slow thaw of the seafloor. It runs on the rhythm of industry, every breath of combustion, another pulse in the planetary ledger. The flux has become continuous, and the air thickens in step with us. The ocean, which once buffered the atmosphere's rise, can no longer absorb enough to keep pace. Warm water holds less carbon dioxide, and modern circulation patterns have slowed, locking carbon closer to the surface, where it continues to interact with the air. In the PETM, the oceans had thousands of years to redistribute the load, pulling the excess down into the sediments. Today, those same processes still function, but at their ancient geological speed. The imbalance widens with every season. Scientists sometimes describe this difference using the image of a clock that measures the flow of carbon rather than the passage of hours. In the ancient warming, the hand moved so slowly that it took entire civilizations of coral reefs and forests to mark a single tick. Each step on that clock represented centuries of adjustment. Today, the hand spins almost uncontrollably. Where the ancient world ticked once in 1,000 years, ours turns with each decade. The balance between carbon input and carbon removal, between warming and recovery, no longer aligns. Still, the same machinery of balance continues beneath the acceleration. Rainwater eats at mountain rock, freeing ions of calcium and magnesium that rivers carry to the sea. There, they combine with carbon to form new limestone on the seafloor. This slow silicate weathering has always been Earth's method of self-correction, but its tempo cannot match what now drives the atmosphere. The processes that stabilize climate require hundreds of thousands of years, yet the pressure builds in mere decades. The air bears witness in numbers that climb too quickly to seem real. In the 19th century, carbon dioxide held steady near 280 parts per million. By the late 20th century, it had passed 350. Now it exceeds 420, each increment a sign of billions of tons released. The molecules are distributed evenly, mingling from pole to pole, erasing borders, marking each breath with the same invisible trace. What the rock record shows as a gradual curve, our instruments now trace as a near vertical line. The shape of the rise is the same, but the slope is steeper by orders of magnitude. It is the same melody played too fast for the Earth's systems to follow. The ancient oceans absorbed, buried, and neutralized the carbon through cycles that required patience measured in epochs. Today, those cycles have no time to respond. The hand on the carbon clock moves faster than the planet's natural defenses can react. And yet, the same feedbacks that once amplified ancient warmth still linger. As the planet heats, permafrost releases its frozen methane, ice melts, exposing darker surfaces that absorb more sunlight. Forests, once carbon sinks, shift toward becoming sources as drought and fire return the stored carbon to the air. The pattern is familiar, but the tempo is new. If the PETM was the earth breathing in, the modern world is a gasp, a sudden inhalation of carbon in a fraction of the time. The total may one day rival that ancient pulse, but its speed makes it something altogether different. The rock record teaches us that the planet will eventually rebalance, but not on human scales of time. The carbon clock keeps ticking, counting every ton, every spark, every molecule. And when its tempo jumps, the feedbacks wake. Long after the first pulses of heat began to rise, the Earth's own machinery stirred in response. The warming did not unfold in isolation. It awakened systems that had slept for ages, quiet processes that had always maintained balance, but now began to tip it further. These feedback loops were the planet's amplifiers, subtle at first, then unstoppable, turning warmth into more warmth. As you saw with methane, one loop can ignite the next. A thawing landscape releases gas, which traps heat, which deepens the thaw again. But methane was only the beginning. Across the world, other engines of change began to hum beneath the surface. They were not violent in motion or sound. They worked in silence, through chemistry, light, and reflection. In the far north, the brightness that once cooled the planet began to fade. For millions of years, ice had been the Earth's mirror, sending sunlight back into space before it could warm the surface. When that mirror cracked, it changed the rhythm of heat itself. Snow melted earlier in spring, and the ground below absorbed more sunlight. The darker tundra and open water drew in warmth like a sponge, heating the air above them. Each melt reduced the next season's reflectivity, and with every lost sheet of ice, the planet held a little more light within its skin. It was an elegant, unavoidable physics. Less white meant more warmth, and more warmth meant less white. That transformation rippled into the atmosphere. Warmer air could carry more water vapor, and water vapor is itself a greenhouse gas, powerful and abundant. Every rise in temperature allowed the air to hold still more of it, and that vapor trapped heat far more effectively than dry air ever could. Clouds thickened, rising in immense glowing towers that reached into the upper troposphere. Some of those clouds reflected sunlight back into space, cooling the surface below. Others, heavy and low, acted as blankets, holding the day's warmth through the night. The pattern was not uniform, but the overall effect was clear. The warmer the planet became, the more moisture filled its skies, and the more energy was trapped inside the air. The oceans, too, began to join the feedback. Their circulation had long been the heartbeat of climate, carrying heat away from the tropics and bringing oxygen to the deep. But warmth changes the density of water, and as polar ice melted, fresh meltwater poured into the sea, diluting and lightening the surface. The great conveyor currents that once sank cold, salty water toward the depths began to slow. Without that sinking motion, less carbon dioxide was drawn from the air, and the deep ocean grew more stagnant. Over centuries, oxygen levels fell, leaving wide regions of the seafloor nearly still. The water above them became warmer, more stratified, harder to mix. A system that had once cooled and cleansed itself began to choke on its own stillness. On land, the forests that had thrived under warmth and moisture began to change. For a time, their growth kept pace with the rising carbon, drawing it in through leaves and roots. But as the heat deepened, the rains grew erratic. In some regions, storms flooded the soil. In others, drought hardened it into dust. Trees weakened, and fires began to sweep across the continents. Each blaze returned years of stored carbon to the air in a single day. Charcoal settled into the sediment, leaving the record of flame that scientists would one day find in ancient layers of rock. These fires did not simply destroy, they reshaped the chemistry of the atmosphere. Smoke and ash darkened the sky, absorbing sunlight during the day and warming the air at night. The fine black particles that drifted down onto snow and ice made them melt faster. Even the soot became part of the feedback, altering the balance between brightness and absorption, reflection and retention. The forests, once the planet's great moderators, began to act as amplifiers. Their own decay became a pulse of heat. Beneath the surface of the seas, a slower loop unfolded. When carbon dioxide dissolves in seawater, it forms carbonic acid, which reacts with the minerals in shells and sediments. This process, called carbonate compensation, acts as a buffer, neutralizing the ocean's acidity by dissolving limestone on the seafloor. But the reaction takes centuries to millennia to complete. When warming arrives faster than that, the oceans lag behind. Acid builds up, corals dissolve, and the chemical balance that once locked carbon away begins to release it instead. The very process meant to stabilize the Earth turns sluggish, always a few steps too late. Each of these systems, the ice, the vapor, the forests, the sea, was ancient, built to keep the planet steady. But under the pressure of rapid change, they began to accelerate the transformation. The permafrost thawed from below while ice melted from above. The air grew thicker with moisture even as forests burned. The ocean slowed its breathing while its surface trapped heat. No single feedback was the cause. Together, they formed a network of amplification, each one feeding the next, bound by the same physics that had once kept the world cool. What made this different from the past was not the loops themselves, but their timing. In earlier warm periods, these responses unfolded slowly over tens or hundreds of thousands of years. The Earth's own rhythms had time to absorb and redistribute the effects. But now, the warming was moving faster than the loops could balance. Each small change triggered another before the first could settle. The ice melted faster than it could refreeze. The forests burned faster than they could regrow. The air thickened before the oceans could draw the carbon down. The planet was accelerating through its own feedbacks, its amplifiers catching up all at once. Satellites now watch this process from above, recording the planet's shifting colors, the retreat of bright ice, the spread of dark water, the rise of vapor, the scar of fire. Instruments detect the faint glow of methane over thawing ground, the shimmer of heat radiating from open seas. Every reading is a note in the same unfolding pattern, the same melody of change that has played before in deep time. The Earth has always responded to imbalance with feedback, a self-correcting mechanism that can either cool or intensify its shifts. But when warming accelerates too quickly, the loops no longer restrain it, they magnify it. The planet begins to echo itself, each process amplifying the next, until the system finds a new rhythm. In that quiet acceleration, the world remembers its old lessons, the same ones recorded in ancient stone, that when warmth comes too quickly, the feedbacks awaken, and once awake, they do not sleep again for a very long time. Life has always been both fragile and unstoppable. It bends, it breaks, and yet it finds ways to begin again. Across the billions of years since Earth first cooled from molten rock, every crisis, every collapse has been followed by renewal. In the great cycles of creation and loss, life has proven again and again that it does not vanish completely. It changes shape. It learns to survive in whatever world it is given. When the Earth fell into its ancient fever 56 million years ago, many species disappeared, but not all. In the darkness left behind, others took their place. Tiny mammals that once hid in the shadows of forests emerged into open ground. Plants that could withstand heat and drought spread their roots farther north. Insects, the small architects of ecosystems, shifted their patterns and adapted to new blossoms. The survivors were not always the strongest, nor the fastest, but the ones that could endure uncertainty the longest. The story of life is full of such paradoxes. Fragility and endurance live side by side. A coral reef, delicate as lace, can take centuries to build, but only days to bleach and crumble. Yet in another corner of the ocean, a few polyps survive, clinging to stone, beginning the slow work of rebuilding. Forests may burn until the ground glows red, but seeds buried deep within the soil wait for rain, sprouting in the ash. The balance between destruction and renewal is the oldest rhythm on Earth, but this rhythm depends on time. In the past, when climates changed, they did so slowly, over thousands or even millions of years. Evolution could move in step with the world, shaping life to fit new conditions. A species that could not tolerate heat might migrate toward cooler latitudes, or evolve smaller bodies, or change its diet. Over long stretches of time, these adjustments created new forms of life. The world transformed, but it did so at a pace life could follow. Now, the pace is different. The same amount of change that once took thousands of years is unfolding in centuries, sometimes within a single lifetime. The air is warming faster than forests can migrate, faster than coral can grow, faster than animals can adapt. Species that once thrived in steady climates now find their homes shifting beneath them. Birds arrive too early for the insects they feed on. Trees sprout too late for the rains that nourish them. Scientists have begun to see patterns in this acceleration. Some creatures are adapting with remarkable speed. Certain butterflies have shifted their ranges northward by hundreds of kilometers in only a few decades. Fish once bound to temperate waters are appearing in colder seas. Microbes, always quick to evolve, adjust to chemical changes in soil and water within years. Yet for every species that keeps pace, many others fall behind. Large animals, slow growing trees, and complex ecosystems cannot move or change as quickly. The world they were built for is disappearing faster than their bodies can evolve. This is the paradox at the heart of life. Its strength lies in its ability to change, but that change depends on patience, and patience is something the modern world no longer offers. The temperature, the chemistry, the rainfall, the rhythm of the seasons, all are shifting together. The clock of evolution, which once moved in harmony with Earth's long ages, now ticks out of time with the planet's new urgency. In laboratories, scientists study fossils from the ancient fevered world to see how life managed then. They find signs of resilience, but also scars that lasted for millions of years. It took the oceans at least 100,000 years to regain balance, and it took ecosystems even longer to recover their complexity. The creatures that came after were not the same as those that had vanished. The forests were filled with new species, smaller and more adaptable, shaped by the heat that had nearly ended them. Evolution had restarted its clock, writing a new chapter from the remnants of the old. Today, that process is happening again, though the page turns too fast. Species are vanishing before they can be named, disappearing in the quiet margins of rainforests and reefs. In the Arctic, polar bears wander longer distances across melting ice, following the scent of prey that grows scarcer each year. In coral seas, fish lose their habitats as the reefs dissolve in acidifying water. Yet within these same waters, new species of algae bloom, new communities of microorganisms rise. Life continues to fill every gap, even as those gaps widen. There is no pause between death and renewal, only the constant reshaping of what survives. The earth does not stop creating, but the patterns it weaves now are different. Where forests fall, grasslands spread. Where ice melts, tundra gives way to shrub and moss. The forms of life shift with the climate, responding to heat, light, and chemistry as they always have. But the question that lingers is how much of the old world can transform quickly enough to join the new. In the ancient past, the survivors of catastrophe became the ancestors of everything that followed. The mammals that emerged from the ashes of the Paleocene fever gave rise to the species that now walk the earth, including us. They were small, resilient, and curious, shaped by scarcity. They adapted to a hotter, more unpredictable planet, and through them, life continued its long experiment. The same patterns may yet unfold again. Life will find ways to endure. It always has. But endurance and comfort are not the same. The conditions that nurture life as we know it are fragile, and the speed of change now presses against those limits. The paradox remains. Life is strong enough to survive the world's transformations, but not always fast enough to preserve what it has already built. The earth will go on creating, reshaping, and remembering, and in that slow rhythm, life will keep finding its way through the heat. The earth remembers in ways we cannot see. Its memory is written not in words or symbols, but in stone, in ice, in the quiet breath of air, trapped for ages beneath the surface. Every mountain, every grain of sand, every fossilized leaf is part of that long memory. It keeps a record of warmth and cold, of oceans rising and falling, of species born and gone. Even the air we breathe is ancient. Each atom of carbon within it has lived countless lives before ours, passing through plants, oceans, animals, and even stars. When we speak of the planet's memory, We are really speaking of the cycles that have never stopped. Carbon is one of its oldest storytellers. It drifts through everything: the shells of plankton, the trunks of trees, the bones of whales, the clouds above forests, the soil beneath our feet. Millions of years ago, during the Paleocene Eocene Thermal Maximum, it was carbon that set the world ablaze with warmth. The same element now circles through our modern atmosphere, the same ghostly signature repeating its pattern. Every atom of carbon is ancient beyond imagination. Some were born in the hearts of dying stars, scattered into space before our planet even existed. Over time, those atoms gathered in the forming Earth, carried in dust and gas, settling into oceans, crusts, and living cells. They have been through endless transformations, from mineral to leaf, from leaf to flame, from smoke to air, and back again. Nothing is ever truly lost. What leaves the earth returns to it in another form, another time. In the deep oceans, carbon sleeps within thick layers of sediment. Each layer tells a story of life that once filled the sea. When tiny organisms die, their remains drift downward, carrying carbon with them, locking it into the seabed. For millions of years, these layers pile up, sealing away the gases of ancient worlds. Some of that buried carbon later becomes the fuels that power our machines today: coal, oil, and gas. These fuels are not merely resources, but fossils of sunlight, the stored breath of forests, and creatures that lived long before humans existed. When those fuels burn, their carbon returns to the sky. It joins the same cycle that once governed the ancient fever, rising into the atmosphere, warming the air, and drifting again into the oceans. The molecules are the same, only their path has changed. They have traveled from the leaves of prehistoric ferns into our engines, from coral skeletons into factory smoke. The same carbon that ended one world now fuels another. The Earth, patient as always, records every turn of this cycle. In ice cores pulled from Antarctica, scientists find tiny bubbles of ancient air. Each bubble is a time capsule, perfectly preserved, holding the chemistry of an atmosphere long vanished. Inside, they find traces of the PETM, the ancient warming that turned the poles into forests. The ratios of gases within those bubbles reveal the pulse of carbon as it rose and fell, as if the planet itself were breathing. Rock layers tell the same story in a different way. Bands of clay, rich in organic carbon, mark moments when oceans lost their oxygen, when life on the seafloor vanished. Other layers, pale and chalky, mark the return of balance, when marine organisms rebuilt their shells and reefs. In each layer, the chemical fingerprints remain, unchanged by time. Even the colors of the rocks, red from iron, black from decay, are reminders of the moods of the earth. Every shift in temperature, every storm and drought, carries echoes of the past. The winds that blow today are touched by the same molecules that once moved through the lungs of ancient animals. The rain that falls on fields has circled the world countless times, through rivers, clouds, glaciers, and seas. The water we drink may once have passed through the roots of trees that shaded dinosaurs. The continuity of these cycles stretches beyond memory, a quiet thread connecting every moment of life that has ever existed. The planet does not remember in grief or nostalgia. Its memory is chemical, geological, physical. It keeps no opinions, only patterns. When too much carbon enters the atmosphere, the world warms. When warmth lingers, the oceans rise and absorb what they can. When the balance tips, ecosystems collapse and new ones form. These reactions are not punishment or reward, only the natural conversation between matter and energy. The earth responds to whatever it is given, as it always has. Humans are part of this memory too. The carbon in our bodies, in our breath, in the air we exhale, is the same carbon that once drifted through forests that no longer exist. With every breath, we exchange atoms with the world, adding our moment to its unbroken story. The warmth that fills our homes and lights our cities comes from the same energy that once fed fern leaves beneath a prehistoric sun. The cycle continues, but now it turns faster than before, accelerated by the choices of a single species. Somewhere beneath our feet, the Earth is already recording this age. Layers of ash, plastic, and steel dust settle quietly into the soil, forming a new stratum that future geologists will study. They will read the trace of our time as we read the trace of the PETM, a sudden spike in carbon, a brief and violent warming, followed by slow recovery. The rocks will remember long after we are gone. The earth never forgets. Its memory is vast, stretching from the first microbes that shaped the air to the modern machines that now alter it again. Every atom, every drop, every grain is part of the same continuous story, a story written not in words but in cycles, where the past and present fold into each other, and even the air itself carries the echoes of what has been before. Far below the waves, where sunlight fades into a muted blue and sound travels as a slow vibration through the still water, the world began to steady itself. After tens of thousands of years of fever, the ocean was still heavy with heat, its chemistry unsettled, its breath uneven, yet within its depths, the first faint signs of equilibrium began to reappear. It was not a sudden shift, no burst of renewal or moment of release, only a gradual uncoiling. The planet's long exhalation had begun. In the earliest stages of recovery, the record shows almost nothing, only a silence in the sediments where life had vanished. Then, in the mud that settled on the ocean floor, the fossils of plankton return, faint and sparse at first. Their shells, built from calcium carbonate, had once dissolved in the acidic waters of the crisis, unable to survive when carbon flooded the sea. Now, those shells appear again, thin but intact, layer upon layer, a sign that the waters were slowly turning less corrosive. The ocean was regaining its balance. The carbonate compensation depth, that invisible boundary where shells begin to dissolve faster than they form, began to deepen once more. In the geological record, this deepening marks the ocean's forgiveness, the slow return of chemistry that could once again sustain calcifying life. With every century, more shells survived their descent to the seafloor. As they piled upon one another, the sediments brightened from rust-red clays into pale chalks, a softening of tone that mirrored the quiet mending of the earth. The isotopes, too, tell of this healing. In cores drawn from ocean basins, the sharp plunge in carbon isotope ratios that mark the planet's fever begins to rise again, not abruptly, but in a long, wavering climb. Each small movement upward records a fraction of carbon being pulled from the atmosphere, locked into shells, buried in sediments, or weathered into rock. The return to equilibrium is slow, its curve drawn gently over tens of thousands of years. The Earth's chemistry, once thrown out of tune, was finding its melody again. As oxygen crept back into the deep ocean, benthic foraminifera, those tiny creatures that live in the sediments themselves, began to return. They had vanished when the waters turned anoxic, their habitats consumed by suffocation. Now, their fossils reappear first in sparse intervals, then more frequently, until the layers are filled once more with their intricate shells. Each shell is a timestamp, a whisper from the seabed, marking the slow rebirth of deep circulation. With oxygen came movement, with movement came life. The same story unfolds in charcoal. During the height of the Great Warming, fires had swept across continents with unnatural frequency, leaving behind thick seams of ash and soot that later hardened into dark bands in the rock. But as the climate stabilized, the intervals between those charcoal layers lengthened. Fire became rarer, less intense. Moisture returned to the air and the soil, and forests regained the damp resilience that had once protected them. The rhythm of combustion, once rapid and chaotic, softened into longer, quieter beats. On the seafloor, the layers of sediment read like a score. The darkest clays mark the height of the crisis, when acid ruled the water and oxygen was scarce. Above them, as the chemistry shifted, the clays lighten and tiny flecks of white carbonate begin to appear. With time, those flecks merge into sheets until the whole layer gleams with the bright remains of plankton and coccoliths. It is as if the ocean had gone from silence to song, from opacity to light. Each millimeter of that pale chalk represents centuries of restoration, the patient accumulation of living dust. Even in the chemistry of the atmosphere, the recovery left a rhythm. Ice cores from later epochs show that carbon dioxide levels fell gradually, the decline uneven but unmistakable. This was not the work of one process, but of many moving in concert. Silicate rocks weathering into rivers, rivers carrying dissolved carbon to the sea, plankton binding it into shells, and gravity pulling it into the dark. Every raindrop, every grain of sand played a part. On land, the record of return is written in pollen and leaf impressions. After the long drought of heat, new forests began to spread across the continents. The species were not the same as before. Evolution had already rewritten the rules, but their abundance marked renewal. In the sediments, pollen grains of palms and ferns fade, replaced by those of temperate trees. The transition is not abrupt, but gradual, reflecting a climate that was cooling slowly, finding a new equilibrium rather than returning to the old. Each proxy shell, isotope, charcoal, pollen captures a fragment of sound, the faint music of recovery. None speak loudly on their own, but together they form a chorus, a low and constant hum that tells of balance restored. The isotopes hum in slow, upward curves. The forams return with the pulse of oxygen. The chalk layers brighten in rhythm with the deepening carbonate depth. Even the silences between charcoal bands tell of peace returning to the land. If one could listen to this recovery, it would not sound like triumph. It would sound like a long-held breath released, a planet settling back into its cycles. There would be the soft crackle of plankton shells falling through water, the faint hiss of chemical exchange between rock and rain, the slow churn of deep currents reawakening after millennia of stillness. The recovery was not perfect, and it was not fast. It unfolded across 100,000 years or more, a span too long for any species to perceive, but it left its trace in every element of the record. Where once there had been noise, the violence of eruption, the rush of carbon, the collapse of ecosystems, there was now rhythm and repetition, a steady pulse returning to the world. The earth never returned to what it had been before. Its recovery was a transformation, not a reversal. The ocean's chemistry found a new balance, the air a new composition, life a new arrangement. Yet the pattern of healing remains visible in the layers beneath our feet. It is the sound of the planet remembering its own tempo after a fever, the slow reappearance of harmony after chaos, recorded not in sound or color, but in the patient, geological language of stone. When the long fever faded, the earth exhaled. The warmth that had pressed down upon land and sea for tens of thousands of years began to ease, not suddenly, but with the softness of a drawn-out breath. The change unfolded slowly, through centuries of gentle cooling, as though the planet was relearning its rhythm. The air no longer shimmered with constant heat. The rains returned with more familiar cadence. The oceans, still heavy from their long restlessness, began to quiet. But the world that emerged was not the one that had existed before. It was younger, stranger, filled with new forms of life that had learned to endure the warmth and to grow from it. The creatures that survived were shaped by hardship. As the climate settled into balance, the small mammals that had once hidden beneath leaves and roots began to explore the open world left behind. The great beasts of earlier ages were gone, and in their absence, these survivors multiplied and adapted. Smaller size had been the key to endurance during the Great Heat, and those same small survivors became the starting points of new lineages. From them, the branches of modern mammal life began to grow, each one finding new shapes, new behaviors, and new homes across a planet in recovery. The forests that rose after the fever were dense with green. New trees took root in soils that had been stripped bare by floods and fire, their roots threading through the softened earth, binding it once more. The light that filtered through the canopy was softer now, colored by the haze of humidity that still lingered from the warmth. Among these trees, new species of plants began to flourish, flowering plants with vivid blooms that called to insects in great numbers. Bees and beetles, ants and butterflies evolved alongside them, forming partnerships that would define the next chapter of life on Earth. Pollination became a dialogue between movement and color, scent and sound. The air itself seemed alive with motion, filled with the hum of a world rebuilding itself through connection. High in the trees, early primates appeared. They were small, no larger than a hand, with grasping fingers and wide, forward-facing eyes. They darted through the branches, feeding on fruit and insects, living lightly in the shade. In these quick, clever creatures lay the beginnings of a story that would one day lead to us. Their fossils, found in the rocks that formed after the heat began to fade, carry the signs of that shift. Bones suited for climbing, teeth shaped for varied diets, brains growing just a little larger than before. Evolution had begun to move with new curiosity, testing possibilities in every environment that the fever had remade. Across the continents, the landscapes changed in color and form. Rainforests spread thick near the equator, dark and humid, while open woodlands began to emerge farther north and south. Grasses and grass-like plants took hold in drier regions, weaving the first threads of what would become future savannas. In these open spaces, small herbivores grazed among the young shoots, and predators followed close behind. Each new adaptation made room for the next. Over millions of years, these patterns of survival gave rise to the ancestors of deer, horses, and elephants, creatures that would later shape entire ecosystems through their movement and appetite. The oceans, too, began to find new balance. As the air cooled and the chemistry of the water stabilized, life returned to the depths. Coral reefs, which had once vanished in the acidified seas, began to grow again in the warm shallows. Their skeletons, fragile at first, strengthened as carbonate levels slowly rose. New plankton species filled the surface waters, drifting in glittering layers that fed the recovering food webs. Fish returned in great numbers, and the color of the sea deepened once more. The deep ocean, which had fallen into stillness during the height of the heat, stirred again with slow, oxygen-rich currents. The planet's great engine of life was breathing anew. On land, the soil darkened with the return of nutrients. Fallen leaves and the remains of dead plants formed rich humus, feeding the roots above. Fungi spread through this soil like threads of memory, recycling the remains of the past into the promise of new growth. Rivers cut fresh paths through valleys, reshaped by erosion, their currents carrying minerals from mountain to plain. The landscapes of the world were being rewritten, every hill and basin reflecting the marks of recovery. Within these shifting environments, the diversity of life expanded faster than it had in ages. Some mammals grew larger again as the planet cooled, while others adapted to niches created by new forests, rivers, and plains. Birds diversified in step with them, their songs filling the air where silence had once lingered. The earth had not returned to what it had been, it had become something entirely different. The heat had been both destroyer and sculptor, erasing what was fragile and revealing what could endure. In the fossil layers that mark this time, the transformation is unmistakable. Tiny teeth, scattered in ancient mudstone, show changing diets and habitats. Leaf impressions preserve the outlines of species never seen before. Even the chemistry of the rocks tells of renewal, recording the gradual fall of carbon levels and the slow cooling of air and sea. Each stratum is a memory of recovery, a reminder that life, when pressed to its limits, does not stop, it adapts. The earth that emerged from the long fever was alive in a new way. It was quieter, greener, and filled with possibility. The small creatures that had survived the heat now carried in their bones the blueprint of the future. Over the next millions of years, their descendants would spread into every corner of the world, evolving into the mammals, birds, and forests that define life today. The fever had ended, but its echoes lived on in every living thing, written into the rhythm of cells, in the shape of leaves, in the memory of air and water. The world that came after was not a restoration of the past. It was the beginning of something entirely new. The world has never hurried. It has turned through ice and fire, through extinction and renewal, always finding its way back to balance. When it warms, it breathes differently. When it cools, it breathes again. Through all of it, the earth remains, shifting, learning, remembering. The last time its warmth deepened by several degrees, the transformation remade the planet. That episode is written in the rocks, measured in isotopes, and preserved in the fossils of vanished seas. For the numbers that define it, see the record kept by the carbon clock we met earlier. What changed then was not just temperature, but rhythm. The oceans slowed, the forests transformed, and creatures reshaped themselves to match the new world. It took hundreds of thousands of years for balance to return. Even so, life persisted. It adapted to heat, to scarcity, to altered skies. From the survivors of that ancient fever came new beginnings, the ancestors of the mammals and forests that later defined the earth we inherited. The story written in their bones was not one of destruction, but of transformation. Now the warmth has returned, but this time its source burns closer to home. The carbon rising through the air no longer comes from volcanoes or thawing seafloors. It comes from the fires we build, from the energy drawn out of ancient stone and buried forests. Each spark, each engine, each field cleared for growth releases carbon that had been locked away for tens of millions of years. What nature once sealed through patience, we have undone in the blink of an epoch. The air responds with quiet precision. It thickens, molecule by molecule, trapping more of the sun's heat within its invisible weave. The seas respond next, drawing in what the air gives, becoming warmer, heavier, and more acidic. Ice that once glittered for ages at the poles begins to weep into the oceans, and coastlines creep inland by inches each year. Forests shift their edges, rivers wander from their old beds. The patterns that once anchored the world's stability start to loosen. The planet answers not with panic, but with memory. It knows this pattern. When carbon fills the air, feedbacks awaken, the permafrost exhales. The seas release their buried gases. Clouds shift and water vapor thickens the air. Each change becomes a mirror of the last. The earth does what it has always done. It amplifies what it receives, adjusting toward a new equilibrium that life must learn to inhabit. But unlike before, there is one new presence woven into this cycle: us. Humanity has become part of the planet's machinery, a species capable of altering its chemistry faster than geology once could. We are the first to see the entire pattern unfold, to measure its slope and name its cause. The rocks and fossils that once told of ancient warming now reflect our own fingerprints. The same signals, acidic seas, thinning ice, rising carbon, echo again, but the hand behind them is human. The earth will adapt, as it always has. It does not end when balance breaks. It reshapes itself. Forests will move, oceans will change color, new species will arise to fill the emptied niches. The planet does not fear warmth or cold. It endures both. What remains uncertain is not the Earth's survival, but ours. Civilizations depend on predictability, on stable rains, steady harvests, and temperate seas. Those are the rhythms now shifting beneath us. The quiet warning is not carved in thunder or fire. It lives in subtler signs: the thinning of ice, the soft rise of tides, the changing pattern of wind. The earth speaks in gradual tones, in signals that stretch across generations. It does not beg or threaten, it simply responds. In time, the record of this age will join all the others. Layers of sediment will trap traces of our cities, the dust of concrete, the shimmer of metal, the faint residue of carbon. Millions of years from now, those layers will tell a familiar story to whoever comes next. They will see a sudden pulse of warmth, a sharp mark in the timeline of the planet, and they may wonder how it felt to live through it. The Earth will survive this chapter as it has survived every one before. The continents will drift, the seas will rise and fall, and life will continue, reshaped once again by heat and time. The planet will endure in one form or another. The quieter, harder question is whether the world that remains will still reflect who we are.